Everyone, welcome to the webinar. We'll see more keep trickling in here, but glad all of you have made it. I hope you're doing well this morning. Welcome to our webinar. We're talking about water distribution system construction and maintenance today. We've got some great presentations for you this morning. So we'll get it right into things. If I can get my slide to move here. This is GoToWebinar, the software that we're in right now. The webinar is being recorded, so this will be available for future viewings on the ADEQ YouTube channel. For you attendees, webcams are disabled. Your microphones are muted, but if you do have questions, if you want to give any feedback or any questions during the presentations this morning, there are two tabs you can do that in. For questions, I recommend the middle tab with the little question mark in a chat box there. That's just to drop any questions. Myself, Ebony Roan, or the current presenter will head on in there and answer those questions. And if any pile up, we'll answer them live at the end of presentations as well. For those of you who are certified operators here this morning, PDHs are available. There will be 4 PDHs if you attend this entire webinar. In the handout section, the little tab with the paperclip on it, there is a file that says agenda. While you're here, be sure to download that agenda file. If you don't download it now and you need it for PDHs later, you'll have to reach out to the OpCert program and we'll verify that you were here and be able to send you a copy then. But for ease of access, I recommend downloading that agenda now, keeping it handy, uploading it to your OpCert portal to use for those 4 PDHs this morning. That's there in that materials tab. Presentations themselves will be sent out later via share file. So whatever email you registered to attend this webinar with, we will send a copy of all of the presentations this morning for you to review later if you desire to do so. And of course, if you have any questions at any time, feel free to reach out to the OpCert program. We got our email there, azopcert@azdeq.gov, or you can call our OpCert line and we are happy to assist you. If you are viewing as a group this morning, make sure that everyone in attendance has registered for the webinar. It's not too late if someone in a group attendance isn't registered to follow the links to register to the GoToWebinar that we're in right now. We want to make sure everyone's registered, and that way we can verify attendance later. So even if a dozen of you are in a group watching the webinar all on one screen, that's perfectly fine. Just make sure that everyone who is in attendance is indeed registered for the webinar. Particularly if you're going to use this webinar for PDHs later down the road. We've got a good group of presentations this morning. I'm really excited. We've got some new and unique content as well. First, we've got 2 presentations from Blake Anderson with Mogollon Water. I'll pass the torch to him here in just a minute. We also have some of our ADEQ staff presenting this morning on the ATC AOC portal, the applications there in MyDEQ. As well as fire flow, hydrant testing, and Dane Whitmer from Consor Engineering will be presenting on the selection and installation of pipes for water distribution systems as well. So it's going to be a pretty jam-packed morning. I hope there's a lot of great information for all of you in attendance today. And with that, Blake, if you are ready, I will pass screen control over to you, and you can go ahead and kick us off.
Thank you, Bram.
Thank you.
Hi, so I'm Blake Anderson. As Bram said, I'm with Mogollon Water Management up here in the Show Low area. I'm a grade 4 operator. I've been in the industry since I was like 21. I have worked with public utilities, private utilities. Now we have a contract operations firm that does a lot of consulting. Really excited for the opportunity to be able to share some content and things I hope are valuable. I got into the industry just like everybody else. I took the first job that offered insurance after I got married and just never looked back, fell in love with it. And you learn a lot along the way. We're going to be talking about a topic that we do a lot of in our industry, and it's going to be more paperwork than anything. We're really good at keeping records. That doesn't necessarily mean that we do anything with those records, but we're sure good at making reams of paper. And so, yeah, we'll be diving in here quick. Bram's going to kick us off with a poll question that we'll look back on a little bit later. Bram, you're welcome to share those anytime if you want to. So our first question is, how many breaks does your system repair per 10 miles of pipe in the ground annually? Yeah, you have a chance, go fill those out. I'm glad so many people know so quickly. This is actually pretty encouraging. Give everybody another 30 seconds or so to answer this question. Okay, looks like it's slowing down. Let's go to the next one then, Bram. What do we think the national average is? Same question, but not just for your utility, but what do you think the national average is? It's per 10 miles of pipe in the ground. Very cool. So have some trickling in here. Last few seconds. All right, Bram, that should cover it. It looks like 3 to 5 is the majority winner. All right, well, let's dive in. Let's talk about paperwork. It's always a fun topic. From today, like I said, most of you probably document your paperwork the old-fashioned way, either jot it down in a binder or have some sort of work order sheet. Even small utilities tend to have a big paper trail. There's a lot of handwritten notes about leaks or repairs. You might have dates or street names on them. For example, you may have valve logs that look something like this. They have, little as-built drawing, says who operates it. You may have something that looks like this for your leak repairs. Little hand sketch, shows a little bit of information about the depth, who worked on it, when it happened, or just general work orders. You start seeing how an actual manifold was built and how something was fixed, so you know parts for the future, that sort of thing. But um, for us operators, this information, we tend to write it all down, but it can be hard to access and actually make action on. And so this information is really critical to have when we need it. And I'm sure a lot of you guys have file cabinets full of stuff like this sitting around the office, but it brings with it two problems. If you weren't the person that was there when the work was done, how would you ever know that that work was performed, or how would you ever find that information? It's good that it was written down and it's not just in somebody's head, but how do you even go about finding it, much less analyzing it? And then if you want to dive into the historic work that's been done in an area, how would you go about compiling all those records to make that decision? And let's just be honest, a lot of this knowledge isn't written down at all. It's just remembered by a longtime operator who's been there for 30 years. And so as we see this silver tsunami continue to happen and this wave of retirements continue to happen, we need to develop the systems to capture that institutional knowledge and then actually use it to make decisions. And so current break log that some people might have that's real simple would just have your date. They say, May 5th, 2020, there was a leak at 123 Maple Street. We patched it with the clamp, water back in service by noon, and that's about all the info it has. It has when it happened, where it happened, and what we did to fix it. And if you have like a big wall map or an old atlas of your pipes, you might also be circling and marking where the breaks happened with pins and notes. But it's pretty simple, pretty standard that we see in a lot of utilities. But this is what your paper logs end up looking like at some point. You end up with these file cabinets full of this information that we know is really valuable and was important enough to write down at some point and save, but it's not easy to process and analyze. And so while these paper logs are better than nothing, they miss a lot of the details. For example, a note might not list what kind of pipe was broken. Was it 6-inch PVC or 2-inch galvanized? What caused it, or how much that repair may have cost you? Does it log your inventory time, your labor costs, your equipment costs? Is it being used to update your maps? If you dig something up and your maps call it out as 3-inch pipe and it's actually 4, Is that getting corrected so people have the most recent and up-to-date information? And then the other thing is it's hard to analyze. If you want to get the trends over the past 4 years, you have to go through find the right file, pull it out, flip through the pages and pages, try to read somebody's chicken scratch from the field, and then maybe come up with a solution. The other issue is it can disappear, it can get ruined by water, can get misplaced, cleaned out of an office when somebody retires. And in summary, our current record keeping system can make it really tough to use any of the information that we're collecting for planning, because all of those pieces of paper are data that can be useful as far as decision making goes. And so why does our data suck? Pardon the language, but pretty much every utility I've ever worked with, that's the status quo. There's incomplete information. So maybe you're only logging the big breaks or like major repairs or the small leak, but the small leaks are never getting logged into a book. Or if you do log a break, you're skipping details. So you may not know why it broke. For example, if it was a freeze or a crack from old age, or if it was hit by a contractor that was running fiber optic in the community. And different people write different things. One guy might jot down that they fixed the main, another might write a whole paragraph for you. And so that inconsistency means that later it's hard to know if these were the same kind of issues or not, if it's a pipe failure, if it was caused by something else. And it leaves a lot of holes in our understanding of what was really happening in the system. And then the next issue is that our data is hard to use. So if I asked you which street had the most leaks in the past decade, you'd have to probably rely on memory or flip through binders, and there's not a quick way to query through all that paper. And you can't calculate metrics like breaks per year on Elm Street without manual counting or just pulling up a lot of different information from different sources. And so that makes it hard to justify funding for projects. So telling your board or city council, I think that this line breaks a lot, is not as convincing as saying this line broke 3 times in the past 2 years. That's 5 times the normal rate, and it's costing us $10,000 versus the cost of replacement over the lifespan is much cheaper. And I think that as we look at the industry, there's kind of a paradox where this isn't true for the people who are listening in that work with private utilities. They have it a little bit harder, but for a municipal system or a DWID, they have the ability to raise rates with a board vote. And so basically it comes down to the justification. And so the fact that we have this gap in infrastructure funding where we know that we need to be replacing more lines than we are, and there's a growing deficit, but we aren't being proactive in doing that and kind of letting these utilities age out. It points to me to a communications issue, that we need to be better about communicating with the stakeholders of why this stuff needs to get done and why it's important to do, because most of our infrastructure, at least in the state of Arizona, was built in the last 40 to 50 years. And so we've been riding on developers coming in and investing the money to build out the infrastructure in the first place. And we're in a time of transition where we need to start moving into just standard maintenance and replacement as these lines age out. And so without having an organized data set that you can point to, you're stuck kind of using gut feelings instead of hard evidence, or we are limited in how effectively we can communicate it. And so that's not ideal when you need the money for the replacements, especially for a large capital project. So another reason that the data sucks is that our numbers can mislead us. And so if we say that pipe A had 2 breaks and pipe B had 2 breaks, they both sound equally bad. But if pipe A is only 200 feet long and pipe B is 2 miles, that's a very different situation. Pipe A is actually in a lot worse shape, but the raw count of just total breaks wouldn't show it. And likewise, if we don't log the cause of the failure, we're going to treat every break the same. So a break that was caused by a customer using a backhoe didn't mean that the pipe was necessarily in bad shape and failing. While it's still a leak repair, it was an accident. It doesn't indicate that it was a failing asset. But a break, on the other hand, that's from a corroded pipe wall or AC pipe breaking down, that's a red flag. And so right now, our data, if we're looking at all, tends to lump everything together, making it hard to tell which pipes are truly at risk and which ones we just simply had bad luck with. And so the good news is that most utilities don't have to start from zero. They already have a lot of information and data on hand. You may have a pile of maps sitting somewhere that somebody's been collecting as-built or logging repairs. Those things can tell you what's in the ground, hopefully pipe diameters, materials, when they were installed, if it's known, is really huge. You may have maintenance logs or repair work orders that have been kept, which list things that have been fixed over the years. Some of you might even report your major breaks monthly or annually to stakeholders. You could pull those reports. And let's not forget the informal data that you and your team probably already know the problem areas in your system by heart. If you've been operating a system for any length of time, you don't need a train like this to say, hey, these are 5 sections of pipe that are really causing us a lot of problems, but you need the data to be able to communicate it and make the justification. So all those pieces of data, when you pull them together, can create a starting point for you. And so somehow, some way, you need to start with a desk that looks like this and take a inventory. So you got to collect all those paper logs, all those work orders, and notes about past breaks, and start putting them together. If possible, even just a simple Excel spreadsheet or a simple table that lists each break that you can remember, general date, even like month or year, the location and what was done. Also, if you don't already have it, gather your basic system stats. So how many miles of pipe do we have in service? If you have just paper maps and you're not using a GIS system, that can be a little bit more cumbersome, but there's a lot of software that makes that a lot easier for you. Also, you're going to want to know what pipe materials are on each section and roughly how old are those. And so if you don't have that information available, you might be able to go to your county records and pull subdivision information, because most utilities are kind of built a subdivision at a time, and that'll give you a rough idea of age if you haven't had any replacements since it was originally installed. And then don't hesitate to use your cruise memory in a meeting. You can ask, hey, do you remember any breaks we had on the west side over the past 5 years? And you might be able to capture some incidents that never got written down. And what you end up with is this baseline data set that might not be perfect, but at least it's something that you can analyze and then start building off of. And then what you do going forward, every time that you have a break, you want to have your records reflect kind of the 5 W's and how. So who, what, when, where, why, and how. And that means who was involved. Was it an in-house crew that made the repair? Was it an outside contractor? What exactly was the issue? Did you have a hole in a pipe? Was there a crack? Was there a leak at a joint? And what was done to repair it? So did you clamp it off? Did you have to cut out a section of pipe? When it occurred, the date and the time, because those things can be relevant. If you have seasonal changes in pressure fluctuation, you can kind of start to point to, hey, we're having more breaks in this section in the winter months. Maybe there's something that we can do operationally to not have so much water hammer. And then you're also going to want to know where it happened. And so an address is great. Marked point on a map with a GPS is even better. And then why it happened. Was it the result of just old age, poor installation, cold weather, water hammer? Did somebody else hit it? Fiber optics, something that we're seeing really commonly where they're boring through lines. And then how we fixed it. And so you're going to want to include in there what materials you used, what parts you used, how long the water was off is great information to collect, and then how much it cost. So if you have to put in some macro fittings, stick a pipe, you've got a backhoe that's out there with a 3-man crew. What's the hourly rate with benefits for that crew? What's the time for the backhoe worth? And what are those parts? And it sounds like a lot, but capturing those details can really pay off once you start to dive into the data behind it. And so you're probably thinking, this sounds like a lot of paperwork, Blake. And I promise you that it's worth it, because when you have detailed and consistent data, you're able to crunch numbers and figure out which pipes have the highest break rates, which failures keep happening, and why maybe even they're happening. And those trends can even help you anticipate the problems and make proactive replacements rather than just keep on band-aiding everything back together. Plus, when you need to actually start budgeting for your capital replacement, you'll have solid evidence. And so you can say this line broke 3 times in the last year. Here's the data, and give visuals that make it really easy to understand why the investment is worthwhile. And so, as one expert put it, it's impossible to make an informed choice without useful data. And so good records will give you the facts that you need to make sound repair or replacement decisions instead of just guessing or reacting. And so to make this all work, you need to standardize how your data is collected. And changing systems and processes is difficult for any organization. Even if you're just using paperwork and you're updating your forms and then having somebody enter it into an Excel form, once the work is done, that works. I personally like to collect it using software. I think it's a lot more user-friendly that way, but you want to design a basic form that could be on an Excel sheet and then that prompts for all the items that are listed. Like I said, we use a GIS-based operation software for small utilities that help us to log stuff from anywhere we're at in the field. And while some software may make things simple, it doesn't really matter what system you have in place unless people are using it every single time. And so you want to make sure that whatever you're doing is easy for your field staff whenever possible, because that's really the data collection mechanism. And so then you want to make sure that everybody's using the same language. And so for instance, you always want to record the pipe diameter in inches. You want to pick cause categories that are standardized, like corrosion or third-party damage. Ideally, that language is the exact same every single time. So when you look at it in Excel or a spreadsheet, you're able to filter using a table and just eliminate the things that you don't want to see, because we don't really care as much about third-party damage if we're looking at, hey, is this infrastructure failing or not? And we also don't want to have one report that says rusted through and another that just says old pipe, because they may mean the same thing. And so you have to train your team, and that's where the organizational component comes into this, that's filling it out. That's just as important as fixing the leak, and it's part of the job. And so you want to keep all those records together, whether it's in a dedicated binder or a folder on a computer. As you can see here, anyone on our staff can quickly and visually see this repair record from their phone in the field. And I think that this is just going to be a lot more important as utility for us who are in the utility space, as we see these waves of retirement coming and a big loss of institutional knowledge, to be able to onboard somebody quickly. We can't take 2 years to get a new operator relatively familiar with the system or where the pipes are at or what size they are. Especially as the marketplace for good operators gets more and more competitive, we should expect that we aren't going to see as many 30-year company men that spend their whole career working for one utility. There will probably be more job hopping as people take higher rates of pay and things get a little bit more competitive at the job marketplace. And we need to utilize the tools to help better equip us as operators with the information that they need to be successful day one. And so I'm sure there's some initial hesitation to changing systems and processes, but I can tell you firsthand that for our guys, we got a relatively young crew. Most of them are under 35. When they go out and make a repair, they throw on their leak boots, they grab a shovel and a probe, and then they pull out a tablet from the truck. And so the goal of any good system and process that's going to be eliminating paperwork, in my mind, is to make it so that it's useful to our operators as soon as possible. And so the result of that is you start seeing this positive feedback loop. So because they're collecting good records, they now have those records for the entire system at their fingertips, which makes it easier to go find a pipe that they don't know, where it's at in the road. If they can pull up measurements really quick and not have to spend a bunch of time exploring for it, they can get the job done faster. But it also incentivizes them to keep the records, because their coworkers are also relying on their record keeping to help them on the next leak that they do. And so there becomes this accountability cycle that comes from the bottom of the organization up, rather than coming from the manager down and saying, hey, you got to keep all this paperwork. It benefits them. But then as the manager, the benefit for us is that while they're out there collecting this information to help with their job, they're also collecting these data points in a standardized way that helps us guide long-term planning. And so the goal is to create a process that's easier and more helpful than the status quo. but you have to standardize things in a way that creates consistency and completeness. That way our data set is ultimately reliable. And so here's a great example of why keeping this information, especially over a long period of time, is really important. So the picture on the right shows a repair that was made to a steel pipe of one of the systems that we operate. This pipe was installed back in the 60s, and it's about 200 foot long. This picture is a different repair on that exact same line. And so imagine you're looking at these pictures in a file folder 4 or 5 years from now. How would you tell which one was which? Or how would you even be able to say, hey, we've had these leaks here? So we took over operations of this specific system in 2023, and in about 18 to 24 months, we had 5 leaks on this one section of main. And because it was such a small segment, it was pretty easy to see that it was going to be a lot cheaper for us to replace the line that rather than keep repairing it. So when we replaced the line, we were really shocked to see just the numbers of repairs that had been done by past operators, but nobody seemed to be talking about or concerned about. And so you can see here in this picture, this is the section of steel line after we made the replacement and folded up. And in total, some of them got ripped off during excavation, but we counted 22 repairs. And so let's say roughly on this 200-foot section of main that's quickly turning into more Band-Aid than it is pipe, each of those repairs costs $250 in labor, maybe $150 for a Band-Aid clamp, and $150 in heavy equipment. Well, if you have 22 of them, that's $12,000 that you've spent on this 200-foot section of main, and really wasted the resources, because the repairs that we made in the past few months, it's not like you can go and reuse all of those clamps. Like once you've made the repair, a lot of those costs are sunk. And so you spend $12,000 repairing a section of main that would have only cost you $5,000 to replace in the first place. And so the total cost to repair combined with the cost of replacement, because you have this sunk cost into your initial repairs, is now over $17,000, which means that the status quo of patching this stuff ultimately ended up costing 3 times as much as it would have been just to make the replacement, once we realized that there was a problem. And so it's hard for us just coming in the past couple of years to say how long this has been going on for. But it's just a good example of when, especially with big organizations, but small utilities too, if you have turnover or people aren't really keeping track of this sort of thing, all of a sudden, what's done with a good heart of wanting to keep rates low and keep the pipe in service as long as possible ultimately ends up costing a lot more, which ends up driving up the cost of your rates, because the cost of installing pipe in 2025 is a heck of a lot more than it was back in 2015. And so this is an extreme example, but it kind of highlights why having good standardized data and records is important, because it allows you to make better decisions and really dive deep into this stuff. And so let's say that the decision to replace isn't as cut and dry for your situation, but you are collecting good data at this point. And so your next step is then to make apples to apples comparisons. So as I alluded to earlier, if you have one main that has 2 breaks, the other has 3, well, which one's worse? And so it's not as simple as it sounds. You have to factor in, what if the first pipe is only 500 feet long and the second is 3 miles long? Well, the longer pipe has more opportunities to break. And also, like, how long of a period of time are you looking at? Are you having 2 breaks in 1 year versus 3 breaks in 10 years? There's a huge difference there. And so you need to normalize your failures by the length of pipe that is in the affected section and the time frame. And so that means you need to calculate a break rate per mile of pipe per year. And by doing that, you can pretty fairly compare pipes of different lengths and see which ones really are breaking most often relative to their size. And it kind of levels the playing field and highlights the true problem pipes, not just the longer pipes or the older systems that naturally are going to accumulate more breaks over decades. And so here's how you do the math for main breaks per mile. You take the number of breaks a pipe has had, and you divide that by the number of years in that data period. And then you divide it again by the pipe's length in miles. You can do foot as well if you'd like, but miles is kind of a good standard rate. For example, let's say a particular pipe segment is 1,200 feet long, that's 0.23 miles, and it's experienced breaks over the last 3 years. That on average is 1 break per year. Now you need to divide that by 2.3 miles, and you get roughly 4.4 breaks per mile per year, and that is extremely high. And so for a lot of us as operators, we may have only worked in 1 or 2 utilities over the course of our career. We're kind of fortunate, or in some ways in the contract operation space, where we get to see a lot of different utilities and see what's working and see what's not. But when you don't have that perspective, you get a little bit of tunnel vision, because that's just the system that you know, and you assume that it's normal because it's your frame of reference. You know, you may know that, or just kind of have a gut feeling that you have a lot of breaks, but because the stuff happens over a long period of times, it becomes normal to you. And so our poll question that we asked at the end was, what's the national average? And so the answer for that is 1.1 break per 10 miles is the national reported benchmark that came out of AWWA. And the true benchmark is 11.1 breaks per 100 miles, but most small systems don't have that kind of pipe in the ground, so it can be so far off, unless you're in the city of Phoenix or something major to really use numbers that large. But as I said, it comes out to 1.1 for every 10 miles. And so for a section like this, if you have 4.4 breaks per mile per year, that's 40 times the national average. And so being able to present that information to your town council or public works director really goes a long way in helping to say, hey, what we're experiencing may feel normal, but it's not normal. Like, this is the signs that things are not progressing in a good way, or we're not replacing our pipeline at a rate that's sustainable. And it also lets you see the break frequency in the normalized way. So a pipe with 4.4 breaks per mile per year is basically breaking a lot relative to its length. And so it's a pretty easy red flag that this section of pipe is in trouble. Here's my bar poll question, sorry. So then the next step is you've computed how many breaks per mile per year that you're having across your entire systems. And so you pull up all of the breaks that you had in 2024, you divide that by the miles of pipe in service. Obviously it's 1 year. That gives you a benchmark of what your break rate is. And so now you have to figure out, of those, which ones do you want to prioritize? And so you do that by focusing on outliers. And so a simple rule is, if your pipe's failure rate is 2 or more times higher than the average for similar pipes or just your general system, it's performing significantly worse than the norm, and that sticks out as a problem. So for example, if your older like CA, cement asbestos mains, tend to average 0.5 breaks per mile per year, and you've got one segment that's clocking in at 1 break per year, then that means that it's breaking twice as often as the others. And so that's a strong signal that the pipe needs replacement, or at least a closer look. And so in other words, the 2X rule helps to prioritize which pipes are truly worse than the pack, and those outliers should rise to the top of your action list. Like I said, I'm sure for all the existing established operators that are on the call, you probably are thinking of 5 streets that you've dealt with for years that need to get done. So I don't think any of this is really groundbreaking, but it's a strong signal that your pipe needs replacement, or at least needs that closer look. So the image that you see on the right is a map of one of the systems that we operate. And so you'll see all of our mains, the lines obviously, and then you see a bunch of these little yellow dots. Those are how we visualize in our GIS system the repairs that we've had. Those are marking the breaks that we've repaired in this system over the past couple of years. And so this system really does experience a lot of breaks. They've got about 34 miles of main line in service, and they experience about 20 breaks a year. So that gives them a break rate of about 0.6 per mile. And so that comes out to 6 breaks per 10 mile, which is 6 times the national average. Obviously, it takes time and money to fix stuff, and so you can't go and replace your whole system at once. But we do want to replace the lines that are the highest priority, so we can make sure that we're spending the limited dollars that we have in the places that they're going to have the most impact. And so I personally love being able to visualize our system this way, because it makes it really easy to see what's going on. And so if you're looking at this image, you can see in the upper left-hand corner, that segment has a bunch of little yellow dots in a small area. And so we are going to focus in on that and then compare it to the rest of the system. And so if we zoom in, we get a closer look. We find that in the past 2 years, we've made 5 repairs on this section of line. So that's 2.5 per year. Additionally, when we look at the data, we find out that every one of those repairs has been on a leaking PVC glue joint. They glued the fittings together because they were cheap. But they, it's the same kind of repair we're seeing on every single one of them, is these joints start leaking, and then we have to put a clamp on the end of it. So when we measure this out on a map, we can see that this section of pipe is about 1,200 feet long, so that's 0.23 miles. And so that comes out to, with 5 breaks over 2 years, 2.5 breaks per year, 11 breaks per mile, which is now 18 times higher, or excuse me, is now 6 times higher than our 18 times higher than our system average of 0.6 breaks per mile. And it's like 100x more than the industry average, which is 1 break per 10 miles. And so at this point, we have to kind of start anticipating that we're going to see this problem continue to get worse, not better, because if there's a joint every 20 feet, that means that we could be looking at 55 more repairs if we continue patching this problem rather than actually address it. And so we want to sink that money into replacement rather than just sink the money into repairs and then ultimately end up having to replace it anyways. And so while that's an extreme example, again, it kind of brings to the forefront the big question that we all have to wrestle with is, when do we stop patching and start replacing? And so fixing pipes is fine for occasional issues. You want to extend the life as long as you can. But at a certain point, it's like patching a leaky boat. It would just be cheaper and safer just to go get a new one. And so if you notice that you're sending your crews to the same sections over and over again, that's a major clue that that pipe needs replacement. And not only do repeated repairs rack up these costs, they burn out your team. I would expect that that's going to be a common question in new hire interviews that you're getting from operators going forward. Is how that's a question at least I would be asking, is how many breaks are you guys experiencing? I personally want to make sure that I'm getting home for dinner and don't like having after hours call outs if I can avoid it. And so people might be more selective, and it may be, just from a labor perspective, something to be prioritizing. But beyond the cost of the repairs or the wear and tear just on your staff and morale, you also have water loss, and you have customer outages that you have to address. And so there becomes a tipping point, and it's not a perfect art, but your break frequency just doesn't make operational or financial sense at a certain point to keep patching and repairing. And so it's our job to figure out what that point is, and where the cost to replace overtakes the cost to repair is the smarter choice. And so you need to figure out your break-even point. And so to do that, you have to turn everything into an annual cost. So on one side, you need to figure out what's the yearly cost of repairing this pipe. So you need to know how many breaks are you having on this per year, per average, and then what does it cost to make those repairs. And on the other side, you need to look at what is the cost of a new pipe to get installed, and then break it down over its lifetime. And so you can annualize the cost of ownership of that asset. And so let's use some just simple numbers that operators will understand. Let's say that we have a new 8-inch pipe that installed is running $100 a foot, and you have 1,000 feet to replace. That brings the total cost to $100,000 for that section. Like I said, these are round numbers, but you guys get the idea. So let's say that new pipe is going to last a very conservative 50 years. 75 to 100 is probably more accurate for modern infrastructure. It may even be able to go longer than that. And so if you break down that $100,000, divide that by 50 years, you end up with a $2,000 per year cost of ownership that covers its useful life. And so let's say each break requires 2 of those 8-inch macros, maybe a stick of C900, 6 hours of labor for a 2 or 3-man crew, plus trucks, heavy equipment. Your all-in cost of repair, and that's hopefully it's not happening in a spot where you're having to patch asphalt or replace a sidewalk or something, because then it could really drive it up. Let's say it roughly comes out to $2,500 for a simple repair like that. That means if you're averaging 2 breaks per year on that section, it's costing you about $5,000 a year in repair costs. And so that's way above the $2,000 that is the cost of ownership per year of that asset across its whole life cycle. And it means you're paying a lot more in fixes than you would just to have a new pipe. And so in that case, replacing becomes a really economical and clear choice. And the saying goes like, you gotta spend money to make money. The same is true with our ratepayers, that we have to be able to spend the money to make those infrastructure improvements at the right time, because you're really driving up the cost of your rates and the cost of service if you're not. Because just patching and patching and patching ends up sinking all this money into something that you're never going to be able to recover, and you're never going to get that money back. And so when it ultimately gets replaced, now you have that much more cost added to it. And so where these numbers start to change is obviously with the frequency. If your breaks are only happening once every 5 years, that would come out to $500 a year for that same repair on average, which is below that $2,000 mark. So you're still making some fiscal sense, and you're okay to keep repairing, but you have to start to quantify that. So and justify, if we're going to keep making patches, is this going to extend the life of the line, or you'll end up sinking money down the road. And so this calculation kind of helps put the dollars to the problem. But remember, it's not just about the money, it's also about the reliability of service to your customers. And so cost also isn't our only consideration in repair and replacement. You also have to look at customer impact. That can tip the scales. Even if you can afford to keep patching, if you keep having breaks in front of the same set of houses and people's water's off multiple times a year, they're going to start to demand a permanent fix, and that they have a reliable service. You'll start getting people showing up to council meetings or board meetings, and they'll get more upset because while they might be grateful that you're making the patch, they're wondering, hey, why isn't the long-term solution being done? And I'm a big advocate for having those relationships with your customers and with the communities that you serve. In my experience, if you can show that the dollars that you're bringing in rates, even if you're having to raise rates, are going back into the system, and you can provide a better quality of service or a better quality of life, the response tends to be pretty good, especially if you can point to specific things. But across the industry, we need to do a better job of championing our wins and sharing accomplishments and success stories, because a lot of times, if we're doing our job right, nobody thinks about the water until it turns off all of a sudden. And so with that, you also have to think about each one of those leaks beyond the customer impact. You're losing water, and so that can obviously create costs, because now you're pumping water out and you're treating it, and then it's just going out on the ground and it's not actually being sold. It also can cause low pressure, contamination risks, and get you into violations and issues like that, and just a lot of headache. Also, you need to look at the criticality of the sections of pipe is kind of a key thing. And so even if you have a abnormally high number of breaks on a small dead end cul-de-sac, that's one thing. But a main that feeds down a central highway, a transmission main, is the one source of supply or a primary source of supply for a whole subdivision. That has a lot higher stakes, and so you need to tolerate fewer breaks before replacement on those sections. And so some places have a rule of thumb, like if a pipe breaks 3 times in 5 years, then they put on the capital replacement plan. All these sort of things factor into your final call, and essentially using the dollar and cents calculations and considering these real world factors help you to make your decision. And so you should end up with a list of 5 or so sections of Maine that you've identified as a priority. And I'm confident that most of you already have this list in your head based on your experience, but with your list in hand, you can start turning into an action plan with budgets and timelines. And so for each of these priority sections of pipe, you need to come up with a cost to replace it and decide ideally when you should do it. So maybe your number one worst main should be replaced next fiscal year, number two the year after that, and so on, depending what you can afford each year. That kind of gives you a framework for budgets, for trying to figure out how you're going to pay for stuff, but also helps you to do the due diligence and planning and design and engineering on the front end. That way you can start getting projects to roll one after another. And so you want to lay out a 5 to 10 year plan, tackling that list in order. And the beauty of having all this data, well, it seems like a lot of paperwork, is that you can justify these projects. So you can show, for example, that pipe A might cost $200,000 to eliminate 3 breaks a year, saving, let's say, $15,000 in annual repairs, and a lot of water loss. That has a big benefit. And so the data from the system on the map on the right is an example of how we use this sort of data to explain to a board how patching pipes was actually a lot more expensive than replacing. And so a lot of the systems that we work with, especially in the contract operations space, they have volunteer board members. There isn't any full-time staffing, so there's no manager that's kind of looking at the stuff. And so a lot of that stuff falls on the governing board, and they operate their systems, or kind of manage their systems a lot like a household budget, because that's what they know. And so they want to put away 10 to 15% every year, but they aren't thinking about the fact that this is such an asset heavy business that they should be factoring in the total cost of all of their assets and then depreciating that over time and building it into their budget. And so if you have 10,000 feet of pipe in the ground, it's $100 a foot, it lasts 50 years, you can use that same math to start to build those things into your budget. But we were able to take the leak repair information from this specific system and put it all together and show it in a way to the board that we were able to say, hey, in the past couple of years, they were spending like 20%, genuinely 20% of their revenue on repairs. And over half of that was going to these service lines that they just kept splicing in and patching. And we explained to them, hey, the cost of digging up this short side service or long side service and splicing in this little section of pipe like you have done in the past is a few $100s. For not that much more, you could just dig up the whole thing and replace it. And so getting people to understand that they should be replacing these things that are failing, not just patching and patching and patching, like you eventually will end up in situations like you saw in those previous pictures where you have all these repairs and band-aids and you've sunk all this money in, and ultimately in your goal to save money for the customer and keep rates low, you're actually causing the cost of service to be significantly higher. And so once they realized the gravity of the situation, because as I said, to them, having that many breaks was normal. And we were in the unique position to be able to say, this is how many breaks they were having per mile compared to other systems that we operate. And it was just astronomically different. They opted to apply for funding and replace some of those services through WIFA. And so we were able to take the data from these that we had been collecting since we started operating it and include it in their application. And so if you need to apply for state funding or loans, being able to present a data-driven plan, so instead of just saying our system is old, trust us, you can kind of show the decision makers that you're proactive, you have a plan, you're tracking this stuff, and you've done your homework, and it strengthens the case to get you the funding that you need. And I'm kind of continually beating the drum that going after grants or forgivable principal loans is great when you can get it, but that shouldn't be your business model. You really need to build in the cost of replacement and set those metrics of, hey, we want to replace all of our infrastructure every 50 years or 60 years. Figure out what that costs today and start building that into your budget. And so for this specific situation of this system, ultimately, it's a 170 connection system. They've been awarded, millions of dollars in funding And a lot of that, I think, was just because we had good data and good information and could kind of advocate for why there was a need in a competitive field with other applicants. And so it's really important for the decision makers on these boards, and I'm proud to say for this specific situation that they hadn't raised rates for, I want to say, 30 years. And that was the goal for them, was to not have to raise rates and to keep them low. Once we were able to show them some of the numbers and actually put some dollars and cents and explain the business side of running a utility to them, they've been really proactive. They've raised rates the past couple of years, and they have a plan to continue to raise them incrementally over the next 5 years. And so they have the political will right now to do 7 years of straight rate increases just to get back to where they should be without having a lot of rate shock. And that really gives me a lot of hope and confidence that they're on the right track and kind of have a path forward and are thinking about these things the right way. And so in closing, keep good records and make a priority list, and then remember that that priority list isn't set in stone. It needs to continue to stay fresh. And so every time something significant happens, update that data. And if the pipe was a low priority, suddenly it has 3 breaks over a couple of years, then its break rate shot up. That pipe may need to move up higher on your list. This shouldn't be something that you're just having to sit down once a year and compile all this data together. Ideally, you put the data collection mechanisms in place that it's really you're getting real-time updates to the things that are happening in your system, and you can take that information really quickly and process it and update your list, rather than having to go dig through file folders and spend a whole day kind of trying to process this stuff. And so then if you replace a section of pipe, great, then you just cross it off the list, and then you see how it impacts your system overall and what those break stats are. Because ideally, if you're replacing those high problem areas, you're going to see fewer breaks across the entire system. And then just make it a habit to review and re-rank that list every year and put dollars behind it sometime around budget season. And so the asset and capital improvement planning is just this ongoing loop. You take the data in, you plan, you have action, new data comes in, you adjust the plan, and you take new action. And so by continually refreshing your data and your priorities, you're always going to ensure that you're focusing on the right things. And so don't forget to acknowledge the successes. As you start knocking out the worst pipes, you should see those numbers go down, and you should be talking about those things and celebrating them, and be bringing those small wins to whoever your decision makers are. And so that's how you kind of get some data-driven progress. And it means ultimately better service for you and your customers, and 3 or fewer AM breaks that you guys have to go out and make repairs on. So if you guys have any questions, I'm happy to answer them. We've got I don't know, 5 minutes or so until we're supposed to be starting the next session. So that's all I have. Thank you. Bram, do we have any questions?
Nothing yet. Ebony just put a little text in the question box. If you do have questions for Blake, it is that questions box. If you're on the browser version of GoToWebinar, looks like a little speech bubble with a question mark in it towards the top right there. Feel free to drop questions. If you don't have any, yeah, we do have 2 or 3 minutes here if you need to run and grab some water or anything like that. We do get one question here from Karen Osterman. Can you suggest software programs for capturing the data?
There's a lot of asset management software out there. Personally, we use a software that's called Ziptility. It's like a GIS-based system that has like work management, inventory, and a lot of those things already integrated. It's geared a lot more towards small utilities, and so once you start hitting 25, 30,000 connection mark, you may be better served by using like an Esri product with their field maps. But for small systems, it's really affordable, really practical, makes it a lot simpler for us. That's what we use personally. So. But GIS, I guess, is one thing I would add to that is just having GIS makes this stuff a lot easier. I mean, ultimately, I'm a big proponent of having my field staff be able to update that stuff in real time and access the data in real time, just because it kind of creates those incentive structures like I talked about. And it also is helpful if we have a customer call in that wants to know what's going on, why wasn't their water turned on, we can really quickly pull up stuff that's not break related necessarily, but hey, we had this person out there at this time, they tried to call and leave you a voicemail at this time because you weren't home and nobody answered, and so they left. We had records across the whole system like that. But especially from a capital improvement standpoint, having GIS and being able to log onto the map itself, the age of your pipe, the size of your pipe, really allows you to kind of dive deep into the numbers in ways that just manually processing, it would be really, really cumbersome. So yeah, that answers it. You guys got
Awesome.
any more?
That looks like the only question for now. To the audience, Blake is going on with the next presentation as well. So if you have more questions for him on this first presentation or any for this following one, feel free to keep throwing them in the questions box and we will get them to Blake. But you're good to continue whenever you're ready.
Yeah, and if people are always welcome if they want to follow up on something later, just reach out to Bram and I'm sure we can get in contact. So cool. All right, well, our next session is on pump and motor efficiency. So this is going to be kind of more on using data to make better decisions. The thing that we see with a lot of small systems is when we come on, there's not a lot of data and there's not a lot of record keeping being done. If they're collecting data, especially on the wells, we typically have at least some sort of records there, but not always. But it's usually always being done on paper. And so that's one of the first things that we do is we start logging things electronically as we're checking our wells and pumps. And then we can use that data to really make decisions that can save a lot of costs and actually cut down on a lot of breaks. I'm pretty proud to say that some of our systems, just by making some small control adjustments and pressure set points, we've been able to drop the number of breaks by 50% compared to what they had been doing previously. Unfortunately, that's kind of just oral tradition coming from the people who were on the board that had been there previously, because they didn't have the data being collected to actually be able to say that. But that's what they report, and so it definitely can be done. And so we're going to start kind of from the end and then work our way back. And so why does efficiency matter for energy? I think that we hear a lot of people in the industry talk about optimizing stuff and green energy, trying to be energy efficient, that sort of thing, but there isn't a lot of instruction on how to do that. And so your energy spend is typically, for at least systems that we operate, one of their largest line items, and it's one of the top expenses that they do have some control over. It's different than pipelines where you have to invest millions of dollars to really start making a dent in repair and replacement categories. There's some optimizations that you can do just by being a little bit more hands-on from an operational standpoint that really can move the needle. It also helps us to see efficiency trends and early warnings. And so you can kind of catch proactively when you're going to have pump failures and when you're going to have well failures, which helps you to plan better and schedule things where it's not an emergency. If you can have a couple months notice that it seems like the motor is trending towards failure, the pump's going out, which isn't always the case, frankly. Sometimes things just go out and that's it. But a lot of times we'll be able to see in the data changes in trend lines that give us leading indicators that this is going to be a problem. And if we're not in our peak months, we tend to take those offline proactively and not run them till failure. And that gives us the time to kind of plan, run off of our other wells for a while, and really do some good maintenance to the well itself while the motor's out of the ground. And so you see these two graphs here below you. This is real numbers from our system that I wanted to start with from two different wells. So we've found, and I believe that you will find it too if you dive into it, that your energy costs can differ by 2 times of how much it's costing you to pump the same 1,000 gallons of water coming out of the ground simply due to your conditioning controls. And so on the left is pump data from a 10 horsepower three-phase well. And we've taken some of this data and ran some basic calculations on it that we'll get into later. And on the right-hand side, you see a 7.5 horsepower pump. It's also a three-phase, but it's a smaller producer from a GPM standpoint. Or excuse me, the left is the 7.5, the right is the 10 horsepower pump. And so even though the one on the left is a smaller producer, gallon for gallon, when we start to break the numbers down, it's significantly cheaper to run. And so I chose these examples to show you just how you can use some of this data to have an indication that your pumps are starting to go out. And so you can see this flat line on the left that all of a sudden has these big spikes. That was a drop in GPM that we noticed, and that also corresponded with an increase in power consumption at the same time. And so you have this inverse reaction. Your impellers start to wear out. As the impellers start to wear out, you have less resistance, so things are spinning faster, and then there's more amp draw. And so you can see that continue to spike and then fall once we made the replacement, and then we have this nice steady flat line from there. On the well 3 graph, you see the exact same thing. You see pretty consistent readings, then all of a sudden this little bump that goes up, and then you make this replacement, and then you see the numbers drop off and stay flat. That was just motor age, I think, on that one, more so than the impellers wearing out. So we didn't see such a significant change, but we were able to kind of recognize it and jump on it early. And so, like I said, when you look at these individually, it really doesn't have the same impact. But when you look at them together, you can see visually just what a big difference in efficiency is. And so you see on the bottom is that same data from well 3. That well is running at 20 cents per 1,000 gallons produced is what the electrical consumption cost is, versus the other well is running at closer to 40 cents per 1,000 gallons pumped. And so it's a 2 times difference to pump the same 1,000 gallons of water out of the ground. Plus the smaller pump is a lot cheaper to replace when the time comes. And so it may not seem that significant if you're just looking at, 20 cents here, 20 cents there, but a well pump may produce 100 million gallons, multiple hundreds of millions of gallons over its lifespan. And so let me put it this way. I don't know if you guys are familiar with the Pan American Highway. It's a series of roads that'll take you from the northernmost part of North America up in Alaska to the southernmost tip of South America in Argentina. And so this road trip that you go on, it's about 19,000 miles in total. And so if you had to make if you were making that trip back and forth to get to 100,000 or 100 million miles, like we're producing out of decent well, that means that you'd have to make that same road trip 5,263 times. And so if you had to do that every 5 years or so, just like whatever your well replacement frequency is, would you want to do that in a Prius, or would you want to take your big dually out there to do it? I guess is what I'm asking. Like, which one would be more efficient? And so sometimes you obviously have a job that just requires the dually, like you need the big pump to meet production. But if you can even do half of your trips with twice the efficiency, it can add up to a really significant amount of savings. And it would be at least worth it to sit down and pencil out the cost. And so we'll dive in and kind of get into like what it takes to figure this stuff out. And so this is an example of a paper well log. It's like super primitive, but probably similar to what a lot of people use. You see your date, your time, your kilowatt hour reading, your gallons reading, and your gallons per minute there. Those are key pieces of information that you should be collecting. On theirs, I don't actually believe they have kilowatt hour readings, but those, for our purposes, those are the numbers that we really need, are your date, the time that somebody was there checking it, what your kilowatt hour reading is. And so that's coming off of your electrical meter. And then at the same time, what's your gallons reading coming off of your well production meter? And so for our purposes, it's not really exactly necessary, but it's also really helpful to log the GPM at the same time, which I'm very confident most of you are already doing, because there is a direct impact that less production capacity has on efficiency. Like I said, if your impeller's wearing out, your motor's spinning faster, that means you have more amp draw. And so it's a really good KPI to help track for your pump health. And so like I said, the good news is that most of you are already collecting this data, but as the example shows here, that some people may not be. But I'm a major advocate for logging this information down digitally whenever possible. If you're already writing it down paper, it's not any more work to do it electronically, and it really doesn't have to cost anything from a software standpoint. This is an example of a well log that has the same information, but allows you to do a lot more with it as an operator. Like I said, there isn't really a need for fancy software. I mean, there's some great products that are out there, but just setting up a shared spreadsheet for each well in Google Drive can be really cheap and effective way to collect data and have to manually re-enter it. Plus, when you have digital access across your team, it means that you don't have to pass a well log back and forth between staff, or if somebody calls with questions, you can pull up the log from the office or wherever you're at and walk the new guy through, what you're seeing or what the problems might be. And then lastly, you can also build in calculations, which we'll dive into in a second, but you can build formulas that are pulling from these different data sources and tracking how much your energy consumption is, how much your new production is. And if people want to reach out offline, I'd be happy to share kind of templates of how we do this stuff, just if it would be helpful. So, but like I said, 3 pieces of information that we're going to be focusing on today is the electrical meter reading, the production meter reading, and the GPM. And if you have that, you can do a heck of a lot. So we're going to just kind of cover the 6th grade math that it takes to do some of this basic analysis. And so first, you're going to look at that kilowatt hour column. That's going to be your electrical meter reading. And so each time you check it, you're going to want to figure out how much power was consumed, like what your energy consumption is. And so that's just the difference between the reading that you took today and the reading that was taken last. Then you're going to want to take the total gallons pumped off of your meter and do the same thing. You subtract the meter reading this check versus the one that was there last. And that gives you your new production number. And then we're going to divide it by 1,000. And so that gives us what's called K gallons, just like kilowatts is K watts. You can now have this an apples to apples comparison, 1,000 watts, 1,000 gallons. And then you divide your electrical consumption by your new production in K gallons. You have to do it, divide your gallons by 1,000. And then what you're left with is your kilowatts per 1,000 gallons, or your energy intensity. And so if we look at this a little bit closer, you'll see highlighted in red is the kilowatts at the top left. Your total gallons is also in red. And then next to those are your energy consumption. And so that's just a basic spreadsheet formula subtracting the previous reading from the one that or subtracting the current reading from the one that came before it and populating those fields for you. Same thing's happening on the new production side for how much water you're actually producing. Then on the far right, you see the same spreadsheet, taking those 2 numbers and doing that formula that I had described and populating all that. And so all those columns that are in gray, the spreadsheet's just doing the math for us. And so what you're left with in that green column on the far right is your kilowatt hours per 1,000 gallons. And so you really want to, as you're doing this, have some sort of spot where people can keep notes on the operating context. So dates and seasons are important, but also if you're changing your tank set points or run times, you want to document that so you can explain what those changes are. Same thing if you get a pump and motor replaced, you want to log when it got swapped out at, what the reading on the meter was, when it was installed, the date it was installed. That way, when you go to replace it next time, you can start to kind of establish some baselines for what should we expect out of this asset. Um, and eventually, just with this small data set, if you get like a 3 to 6 month window, you probably have enough data that you can actually start making some decisions. So now let's break down the cost of how much power does it take to pump 1,000 gallons, or as we call it, energy intensity. So your next step is to convert that energy intensity into dollars. And you want to do this for two reasons. One, as an operator, your time's valuable and you want to know that the potential savings are worth you making changes or investing in more efficient equipment. There's pretty significant savings that I think can be found, because a lot of utilities that we see tend to just have a bunch of wells fired to fill a tank, and they aren't really thinking about how to start running things in lag and lead functions and optimize it. I think that there's a lot of low-hanging fruit across the industry here. But the other reason that you want to convert it into dollars beyond just your own time and investment is you're going to have to explain this to whoever the ultimate decision maker is that controls the purse strings, and get their attention and get buy-in. And so being able to say something in dollars and cents instead of saying something in, kilowatts or, 1,000-gallon units really has a lot more impact. And so for some quick math, if you want to pump in for your power for a kilowatt hour at about 10 cents per, that comes out to 2.5 kilowatts, costs you 25 cents per. If you have 2.5 kilowatts per 1,000 gallons, that means that your total cost is 25 cents per 1,000 gallons produced. You can check your own electric bill to see how much they're charging you in your local area. Obviously, time of use is another factor. Depending on the size of your setup, you may be able to get better commercial rates. But our local company, it's about, I think it's 0.098. And so that's why we use 0.1 just as a quick reference point, so you don't have to go look it up yourself if you want to do some quick calculations. But you can see on the graphs below how this can get broken down. And so on the left-hand side, you see that same kilowatt hour per thousand with the electrical cost added. And you're going to notice some changes over time. And so on the well one, the blue line, you see this big spike, and then you see this big drop, and then it kicks back up, and then it kind of maintains flat. That was a well replacement that was going on. Same thing with well two. You see this big spike and big drop. Well three just as steady as it goes, and then well four starts off relatively steady, kind of dips and rises. But then you can see it start trending up over time and makes this big, it's starting to increase and really get outside of what the norms are. And so where it ends versus where it started, it's running at about half the efficiency that it was. And so those are the kind of indications that we're looking for in that specific example that tell us, hey, something's going wrong here, or something's not right, something's changed in the system. And then that drives us to do a little bit further investigating and trying to figure out and be proactive about how to go about fixing it. Well, when you look at these from a dollars and cents standpoint, it's pretty clear that well three is the cheapest, and so just run that one, right? And not the others. Well, here's why it's important that operators like us make those decisions instead of people who are just bean counting. Look at the graph to the right. It's the same data, but instead of looking at the cost per 1,000 gallons, we took the daily average production and energy or energy consumption, and then we put a dollar amount to it. And so basically, like, how much is this well actually producing each day? And we're not running in a vacuum where we can just always run the cheapest well all the time. Practically, like, you can't just run small pumps to operate a system. You have multiple wells because you have to be able to meet the demand of the system. And so that's where operationally it's incumbent upon the operators to start to make choices that can maximize the usage of your cheapest wells, but you still need to be cycling and running your system. And so for us, like a 4th of July weekend up here in the White Mountains is the busiest time of year, and we pump, 20 times more water in that week than we would in any other week of the year. And so it doesn't really matter to us. Frankly, which well we're running at that point, we have to have them all on because our priority one is just keeping water in the tanks. Priority two is then doing that as cost effectively as possible. But the priority has to be keeping up with the demand in the system. And so you have to start looking at seasonal changes depending on your capacity and what demand is at, that maybe you're running things differently in your off season months than you are in your peak season months. Um, and so you've got a few different factors that drive pumping costs. There's basically four levers as an operator that you really should understand, and you probably do have some level of influence over. Your starts and stops first. You guys probably already know, just being in the industry, that your starts and stops are not only your highest energy demand, but they have a big impact on how long your motor will last for. And so, it's abrupt to get something going from uh, 0 RPMs to over 3,000 RPMs in an instant. And so that's a lot of wear and tear. If you can just get that number to change by 10-20%, it can be pretty impactful, not just on your electric bill, but also on just extending the life of your motors. So that, kind of like we talked about in the last section, that life of the asset that you're putting in spread out over 5 years. If you can get that to 6 years, that's a 20% less cost over its life cycle. And so then there's also your general condition of your motor and impeller, or even the well itself. So if your water level downhole is lower right now than it was 5 years ago, that means that you're going to have less head pressure coming into the inlets, which means that you're going to need more energy to lift that water than you did previously. There's also system hydraulics. So how much head are you pushing against? Some of these things you just can't do a ton to change, like the elevation of your tank is pretty well fixed. But you can look at things like, does my manifold have restrictions that are increasing head as we're trying to push out a bunch of water? If you're pushing into a pressure zone with the booster, do we have to run it 55 to 60 psi? Could we go down to 50 to 60 and keep everybody in above minimum thresholds and gain better efficiency? Can you move those set points to really match what your pumping curves call for? Those are all things that you can kind of start to look at from a system hydraulic standpoint. And then there's also your motor type and your controls. Single phase motors are typically going to be a lot less efficient than your three phase. But there's also your VFDs, your transformers, all those things can have a major impact. Kind of like I talked about with the starts earlier, going from 0 RPM to full speed. VFDs allow you to slow start or soft start, it's called. So it spins up over 45 seconds, minute, whatever it is. Those are some things that you can add that really do gain some efficiency and really get your assets the most life. And so, like I said, all this stuff, you don't really need a lot of fancy analytics. You just need to operationally to be paying attention and be thinking these things through, take a few of these numbers down, and then start using some thresholds. And then if you do run the numbers and you start to see some odd trends, the question you should be asking yourself is, which one of those four levers has started to change recently? So did our starts and stops rise all of a sudden? Did our drawdown increase? Are we seeing like water levels drop? Did a VFD get programmed differently? Are we just having an impeller wear out? And so the 80-20 rule kind of applies. Most waste comes from like a simple few missettings or degraded assets, but we'll dive into those deeper, and really a little bit of time can have a pretty significant impact here. And so why your startups matter. Your startups draw about 6 to 8 times the running amps is what your well does actually once it gets running. It's your hardest event on your bearings, it's your hardest event on your impeller, and it can waste a lot of energy and life. And so you can adjust these things or modify these things with different control functions. You can increase the set points on your tank, so you drop an extra foot or 2 feet to before it starts filling, to kind of make this big curve rather than a bunch of short stops and starts. You can set up your wells to run in lag and lead, so you could have your most efficient well run after the tank drops a couple feet, and then a foot lower than that. If that one's failing to keep up, you can have another one go. You can look at time of use and letting things run a little bit lower and fill up overnight. It just really is situational and depends on how your system's designed and what the control changes that you can make are. But you see this graph on the right, we pulled this out of our SCADA system, and you can see these bars rise and fall 3 times over a 24-hour period, which doesn't seem like a lot, but when we do the same graph over a 1-month period, uh, all of a sudden those little spikes start to add up. And so you think about that not just over a month, but over 5 years, how many times that is just cycling on, off, on, off, on, off. Um, it becomes really, really impactful if you can change those even by 10, 20%. That can be thousands of starts that you didn't have to have over a period of years. And so a good rule of thumb is you take, if your starts or stops per day suddenly increases by 25% and you don't really have demand change, you're going to want to check your sensor levels, your bladder tanks to make sure that there's air, check your control programming. Um, and beyond the cost of electricity, like I said, this will really prolong the life of your motors, which can add up to a significant amount of money, especially for people who are coming from larger utilities that have really large motors. Even just getting a 10 to 20% lifespan increase. And so as an operator, I'll be the first one to admit that when I'm checking wells, I'm really just getting a snapshot of the 10 to 20 minutes that I'm there at that specific day. And if you don't have hour meters or start meters on your panel that you're logging, it can be really hard to tell how often your pumps are cycled. And so we just brought on SCADA for a couple of our systems, and one of the sites had a booster in it, and the vendor was nice enough to call me after we got installed and make sure there wasn't some sort of problem with the programming, because the booster had ran over 180 times that day. Um, we were able to make some control changes to get that number down from 7 to, I don't know, 75 to 100 times. But unfortunately, like, that system just is set up the way that it's set up and sized the way that it's sized currently. And so it'll take some investment and changes to really get it any lower than that. And so you just do what you can operationally. But if you had asked me how often I thought was cycling just based on being in there and checking wells, I would have thought 50 times maybe. But it's hard to kind of extrapolate what's this doing over a 24-hour period when your only frame of reference is just this small period of time that's in there. If the building had smelled different or it felt hot in there, I could have told you that sort of stuff that would have indicated booster health. But your starts and stops, if you don't have a mechanism to track it, gets pretty difficult. And so um, especially for operators that are running smaller systems, I really recommend looking into SCADA if you don't have it currently. It's amazing how much data you can get and how cost effective it's gotten with these new cloud-based cellular units. Like I said, when I first started out in the industry, the municipality I was working at had spent, I want to say, over $100,000 to have this big server panel with a computer that was controlling, I want to say it was monitoring one well and one tank site, or maybe 2 wells in a tank site. But it was genuinely hundreds of thousands of dollars. It's a tenth the cost of that, and is this big. Just like a lot of other technologies, those price points are getting a lot simpler. The hardware is getting a lot more standardized, and it's getting pretty cost effective to actually do SCADA and be able to do some of this stuff, even if you are in a small utility. And so not only can the SCADA help alert you of problems and collect these just vast amounts of data, because it's like having somebody at your well site checking things 24/7, 365. But it also allows you to program a lot more specific controls to optimize how the system operates and what's getting turned on and when it's getting turned on. So you can set wider tank dead bands. You can set it up to run your wells in a leg lead setting. You could even install like vibration and temperature sensors now on boosters or turbine pumps that can monitor in real time what your motor health is. Um, I'm sure a lot of people have seen Pump Curve over the years going through their operator certification things. This is really key information, especially when you go to replace stuff or look at making improvements. It's also a good way just to keep an eye on what the health of your assets are. And so to read it, you need to plot what your flow rate is. And so that's going to be Q. That's at the very bottom. You just, if you're 200 gallons a minute, you run a line straight up. And you're measuring that off of your meter. And then you're going to also take your total dynamic head. So that's going to be your discharge reading converted to feet. And so that'd be times 2.31 plus the elevation difference from your well inlet minus the suction head. So basically, wherever your pumping level is coming from, plus the system pressure that you're pushing against, all that adds up to be your total dynamic head. I mean, you can get a little bit more into the weeds and have it more complicated than that, but that's basically it. How high are we lifting this out of the ground? And then once it gets out of the ground, how much pressure are we pushing against? And so when you get those numbers together, you want to be looking at those efficiency bars with the percentages. And so you see right around the 250 gallon mark against 50 feet of total dynamic head. If you see where those two lines intersect, you start hitting that 80% to 81% efficiency range. Nothing is purely efficient. You're never going to have 100% efficiency. There's always going to be loss to heat or things along those lines. But you want to stay in those ranges, because if you start getting out of those specs with the wrong size of pump, you're going to end up losing, way more electricity than you need to. And so I recommend keeping a curve sheet at each one of your sites, and just keep a copy of it there. And each month or quarter, even annually, but quarterly probably be best, log your flow, log your total dynamic head, and then log your amps. And if you have a VFD, probably what the speed is, and just circle where that point is on the new operating point. And so good rule of thumb is if you're 50% off that best efficiency point, that's at 80% mark in there where it's going to be running at its most efficiency, see what's changed. And if that operating point, if you start to see it drift over time, try to figure out what changed to make that happen. Do you have a difference in system pressure that you're pushing against? Is there a valve restriction? Did you change something with the speed? Are your pumping levels changing, or is just the motor rolling out? So that best efficiency point is where your pump is the most efficient and really the happiest mechanically. If you sit far away from there, you're going to expect a lot higher energy use. You can get into heat and vibration. There could be just kind of a lot of problems that come with having the wrong size pump for the wrong application. For example, that one of those systems that I showed you on the map previously, when we took over, they had a well that had been offline for a number of years, and they were just kind of cycling it manually just to keep it going, but they didn't actually use it in production because it was using so much power. And so how it was set up was there's a 15 horsepower pump, submersible pump downhole that pumped up into a 7.5 horsepower booster pump, and then that pushed it out to the system. And so we started looking at it, and I guess sometimes you got to draw stuff for me with crayons, but I wasn't afraid to ask the dumb question of, hey, why do we have this booster pump here? Why not just use a single well motor? Nobody really had a good reason beyond that's just the way it is. Nobody knew why that was the way it is. That's just how it had been done. And so we got this well back online. We got set up with automation, and we went in and replaced that 15 horsepower motor with a 20 horsepower motor, and then we just eliminated the booster entirely. And this is not an exaggeration for a number. We saw a 700% improvement in energy efficiency from the day before to the day after, just from making that one change. It paid for itself in no time, and now they have a production source that's reliable and can run, and it's just running in automation like it should be, instead of just being kind of cycled to have on standby. And that's a heck of a lot cheaper than having to go drill a new well. And so there's, I think, a lot of low-hanging fruit across the industry if we start actually asking why things are the way they are and thinking how can we go about changing it. So another metric that you can track is what's called your specific capacity. And so this is a little bit different. You're looking not just at your well motor, but you're also looking at your drawdown and what your pumping levels are. And so your specific capacity, it's a pretty simple metric. You take your GPM and you divide it by your drawdown. And so your drawdown is the difference between when the well pump's turned off, that's your static water level, and your kinetic level is, or pumping level is when the well's running. That's where the water level drops to. Whatever that changes is your drawdown. And so it's a really good early warning KPI that tells you hey, something's changing here. And a good rule of thumb that we like to use is that you should be alerted at like 15 to 20% change. And you really should be looking like at rehab if you have a 30% change. So that would tell you basically if your GPM changes by a significant amount, it's going to affect that number. And then also if your well capacity itself is going to change, where you're seeing that drawdown drop, that's going to have a really big impact on those numbers as well. Um, your drawdown, especially for people that are in more water scarce parts of the states, is something that we'll talk about a little bit more extensively. But it's really valuable information to gather. And so we don't just want to look at the motor itself, but we also want to look at the actual well, the casing. Are we seeing the capacity start to change over time, and things start to really get out of kilter? We have a way to track that. And so just a simple one-page sheet that kind of documents that, similar to that pumping curve, can kind of create some triggers to do a little bit more investigation. And so to do that, like I said, you'll be needing to measure your static levels, your pumping levels, and what your drawdown is on a relatively regular basis. You want to use the same measuring point, same method when you do it. And ideally, you're doing it pretty regularly because you want to be able to know seasonal impacts, demand changes, and compare year over year. And so I hope most of you are familiar with one of these, but sounder. But these are a useful tool to do drawdown tests. You also can do air tests, which is what I prefer. I think it's just a lot easier. But you want to log a couple things. You want to get your kinetic water level, so that's your pump running. So get it to turn on and run for an hour to 2 hours. And what is the water level at just in normal conditions? And then you want to do your static test. And so let the well pump sit for, I would say, at least 2 to 4 hours offline and recover, and then check your levels. And then your drawdown is your kinetic level minus your static level. And so from there, you can start to figure out like what your sustainable rate is, especially if you want to do step down testing. Step down testing is where you basically put a pump down hole and you run it at different flow rates, and you see how your water level reacts, and it'll tell you your overall capacity. That way you can get the most out of your well, but you're also running in a way that's sustainable and you're not going to run into cavitation or that sort of thing. If you are having like drawdown issues or just groundwater decline in your specific area, step drawdown tests and like regular drawdowns are really kind of critical information that you should be gathering. But it'll reveal to you, like I said, how your drawdown will change depending on the flow and help you to set a little bit more sustainable rate. But let's say that you're just seeing a decline. It's not necessarily always going to be groundwater decline. It can be a lot of times that your casing's just getting plugged up or fouled. And so when that happens, and you're, ideally in a situation where you've got the pump pulled, it was a planned pull, and you have a little bit of time to actually get in there and do some inspecting. I always recommend that when we pull a pump or motor, obviously we inspect the pump and motor, but we do a video log downhole just to see what things are looking like. Depending on what we see down there, what we find, we'll typically brush and bail, but there's also additives that you can put down in your casing to break things up. You can use mechanical methods that kind of hit the slime or like loose fines. Acid works good on carbonates. Oxidants or dispersants are good for biofouling or iron. Really, that's questions that you should be talking with your vendor about what method it would be most effective, what contact time you should have, what they expect the improvement should be. And then really I would track your pre and post results. So video log before and video log after. You should have an idea of what your yields were from previous times it's been done, and then be able to compare that to after it was done, at that time. And then just if you are going to especially put anything down hole, protect your equipment, protect your customers, make sure that you're neutralizing the chemicals that you're dumping to and disposing per whatever rules that are applicable. But doing good maintenance on your casings can get overlooked, especially if you're just moving from crisis to crisis and we have to get this pump back in the ground. But it's like going to the dentist. You know, there's a lot of different tools they can use, but those regular routine checks really make a significant impact over a long period of time. And then after you're done rehabbing stuff, reset that baseline for your specific capacity, reset your kilowatt hours per 1,000 gallons, and especially if you can show a big change, you know, like I talked about that 700% energy efficiency, share that stuff with your management, you know, share, like, really, you know, be able to document and share the wins and share the successes and like why it's worthwhile to take the time to do things right and invest in maintaining the assets, not just building new ones. Another really simple thing to monitor, and like I said, some of this can be done now with SCADA sensors pretty cost effectively, but is temperature. Heat is just energy being radiated, and so it's a pretty good indicator of motor health. Obviously, if you have a submersible pump, that's not really a thing that you can keep an eye on, but for your booster pumps, for your turbine pumps, getting one of those cheap infrared thermometers and monthly logging the reads for that, listening for your bearings, feeling for vibration. I like, for a monthly check, the idea of pulling your amp draw while everything's running and just logging that stuff over time. It can tell you a lot. And I would recommend investigating if you see your surface temps get over like 180 degrees on your motor housing, on your heat sinks for your VFD, and then just be sure your building should be clean. Keep your louvers clear. Keep your fins clear. Those things really can help prevent a lot of overheating. And those small, consistent checks can prevent a lot of big failures. And so, like I said, SCADA can do a lot of this stuff now, but simple Harbor Freight infrared thermometer for $30, you can kind of start logging that information. And so here's kind of the triggers in summary of what we want to look for, and basically numbers that are going to cause us to start looking at like, hey, we need to make this into a work order and actually get somebody, we need to do a little bit deeper dive. And so if we see our kilowatt hour by K gallons increase by 15%, we're going to go inspect stuff. If we see our starts and stops per day increase by 25%, and there's not a corresponding change in demand, we're going to go check our controls and try to figure out if something's changed in the system, if there's a valve that got left off somewhere and the system hydraulics are causing things to not flow the same way, if there's restrictions, that sort of thing. And then also, if we see a drop in our specific capacity, like I said, 15 to 20% on the specific capacity, really 30% I would just plan to rehab. Same thing with the kilowatt hours per 1,000 gallons. If you're seeing a big change like you're seeing on this graph, like you see around the 40 mark, how you start to get to those spikes, around the, let's say, 45 mark, that's probably the time to be saying, hey, we need to get a hold of the well driller. What's our horsepower? Is like, we know something's going on and we should jump on it relatively quickly. Sometimes, you know, there's theory and there's real world. That's just not practical for what you have going on operationally. You need that well to get through a demand period. You have another well that's being down and you need to ride it out. Those are just the decisions that operators have to make kind of along the way. And then for your run plan, as we discussed, you want to prioritize your lowest kilowatt hours first, and your use storage as much as possible to kind of shave off your peaks. So if you can, if your tank is running like a 3-foot deadband, if you can expand that to 4, 5, 6 feet, it doesn't really impact the PSI that much. And so do you need that much storage capacity? Could you use your storage capacity a little bit differently? Could you set up things to run into lag lead function? Could you set up winter and summer operating cycles with different programming functions? Could you use your storage overnight? You know, could you have a well that kicks on in off-peak hours and fills the tank till full before morning, and just runs consistently? Don't forget, if you are going to look at doing like lag and lead functions, that you really want to alternate those lag pumps so they are getting some movement on the bearings. You want to keep them healthy, but you don't necessarily have to have them running constantly with everything on, everything off, because you're going to end up burning up money just running your inefficient units. And then document all this stuff if you're making these operational changes. Like I said, I don't think there's anything wrong with asking the question of like, why are we doing things the way that we're doing it? You know, why is our tank set with a 3-foot deadband instead of a 6-foot deadband? But if make it so in the future people don't have to ask that question, you can explain the rationale and how it was thought through and what the numbers are and what the metrics are, so your predecessors don't have to go through the work of doing the stuff that you guys might be doing. So I'm happy to take any questions before the next session if you guys have any. Thank you.
I'll give just a minute here for some questions to come in. Thank you very much, Blake, for the presentations.
Well, hopefully it was helpful.
Absolutely. And I will echo again, make sure you do download the agenda, especially if you're a certified operator. If you're on the browser version of GoToWebinar, up towards the top right, there's a little tab. It's a piece of paper with a paperclip next to it. It says materials. If you hover over it, click on materials, download the PDF in there. That's the file that you'll need to upload to your portal account to get the 4 PDHs from this webinar this morning. So make sure to download it now. And also on that agenda, there is email contacts for all of our presenters today. So if you do have a question for Blake that you think of or are working on now and you want to follow up with him later, that'll be a good way to reach out.
You're welcome to.
I do got a question here from Steven. He says, what is an ideal drawdown?
It really depends a lot. I wouldn't say that there's an ideal, but what you want to see is it's constant. And so you should know what your drawdown is, and you shouldn't see it fluctuating a lot over time. If you have the same size well pump in there as you had previous years, if you're starting to see a change in your drawdown or your just pumping levels, anything like that, it's going to tell you one of two things. Either we have less water down hole, or the capacity of the well, something's fouling up the perforations, your packing's getting plugged up. But it really just does change a lot depending on the size of the motor that you have. If you have a well pump that pumps 1,000 gallons a minute, 2,000 gallons a minute, you're going to see more drawdown typically than you will in a smaller well. But it fluctuates a lot on local issues. So the big thing is just collecting the information. Good question.
Awesome. A question from Johnny here. In your experience, is there a brand of pump that you recommend over another?
We've had good luck with Grundfos, but I wouldn't say that I would feel confident in saying like that's the best or anything like that. I kind of would point back to the vendors and ask for data. You know, I hope that as we continue to do this stuff and log it, 5 or 10 years from now, I could give a lot better answer where we could say, you know, pump A versus pump B. But I just would like to see the data behind it. But we do seem to get a little bit longer life out of the Grundfos. They're a little bit more expensive. We've had some of our systems that kind of just put in the cheapest one possible, and that was pretty significant change there. But I guess I really don't have that hard of a stance. So.
Awesome. Well, that looks like it for now. Cool. Blake, again, thank you so much.
Yeah, thank you guys. Appreciate the time.
Perfect. Okay. Up next, we have a presentation on MyDEQ ATC AOC applications. Nicole, I'm going to pass screen control over to you. Nicole and Stephanie will be going over this topic for us. I see your presentation, so you should be good to go.
All right, thank you, Bram. Good morning, everyone. I'm Nicole Rubenstein. Me and my colleague Stephanie Wong are both associate engineers with the Safe Drinking Water Engineering Review Unit. We're going to be discussing the approval to construct and approval of construction application process and how this has changed since we've gone online and started utilizing the MyDEQ portal system. So brief agenda for our presentation. We'll do an overview of the approval to construct and the approval of construction. We'll go over the process with MyDEQ. We'll touch on the water system facility forms as well as pre-application meetings. So to start off, if you're not familiar, what is an ATC? It's a certificate issued by ADEQ or a delegated authority that allows an applicant to construct, modify, or make an alteration that will affect the treatment, capacity, water quality, flow, distribution, or operational performance of a public water system. So essentially, when a public water system is installing a new water line, storage tank, booster pump, well, chlorinator, treatment plant, those sorts of things, they'll have to get an ATC permit and an AOC permit. And ADEQ has delegation for a lot of the state, but there are a few counties and cities such as Maricopa County that has delegation. So applicants in those areas would have to submit to their delegated authority for that ATC and AOC permit. So the first step is to complete an application through MyDEQ. This used to be a paper process where we had a paper application that was emailed to our group email, but since we've launched MyDEQ, this is now an online process, so the application is completed through the portal. There are different review fees associated with the ATC permit. It's based on what component and the sizing. So I've included a link for where those design fees are listed so you can check and see exactly what the cost would be for whatever component you're submitting an ATC application for. We do offer priority review, and it costs double the standard review fee, and it does have to be approved by us depending on our workload capacity. So it's not a guarantee that we can offer the priority review, but it is an option that we can offer to try and help get an expedited review for our applicants. State agencies don't have any fees since we're a state agency. And so the next component for the ATC is a design report. The design report must be stamped by a professional engineer on the cover sheet. We also require construction drawings that are stamped by a professional engineer. The only exception for that is that federal agencies do not require the PE stamps. For a new well, a new source analysis is also required. And for a water line for a subdivision, we also require a water service agreement. So those are the main components that are submitted for the ATC application online. So moving on to the approval of construction. So an AOC is a certificate issued by ADEQ or a delegated authority that allows an applicant to operate a public water distribution system after construction and final testing have been completed. So once you get the ATC that approves the design to go ahead and construct that facility, and then once that construction is completed and all the testing is completed, then the applicant comes in for the AOC permit. And once that permit is issued, then they are able to operate that facility. So one of the changes with MyDEQ for this process is that before the AOC application can be submitted on MyDEQ, the applicant must report the start of construction date on MyDEQ. So that's a new step that the process now requires. But once you've reported that construction start date, it's very quick and simple to do. Then you can go ahead and once you're ready, submit your AOC application. So again, the application is completed through MyDEQ. There are no fees for the AOC, so the fees are just at the ATC stage. So if you were to request and get approved for priority review at the ATC stage, that would also apply for the AOC stage. So priority review for ATC will also lead to a priority review for the AOC. So the main components that we request for the AOC are as-built drawings stamped by a professional engineer. There's pressure test and chlorination test data that is required depending on the component. So some of the components will require that, some of them won't. All components do require the bacteriological lab results that are less than a year old. And occasionally there might be an additional requirement that was stated on the ATC. For instance, some ATCs will include that the fire flow test will be submitted at the AOC stage instead of the ATC stage. For treatment, and O&M is typically required sometimes at the ATC stage, sometimes at the AOC stage. And sometimes the AOC might be contingent upon another AOC approval. So there can be additional requirements, but those would be stated in the ATC permit. So they would be known well in advance of what would be required at the AOC stage. I'll give an overview of the MyDEQ user roles to sort of familiarize ourselves with some of these new terms that we have now that we use MyDEQ. So the responsible corporate officer, the RCO, is the main account holder. The designated responsible officer, the DRO, can act on behalf of the RCO. The RCO or the DRO, either of them can assign a data entry or submitter to submit applications on their behalf. So typically the RCO will add the engineering firm with the data entry or data submitter role, and that'll allow the engineering firm to submit the application for them. The RCO or DRO still will certify the application. So the engineer can fill out the whole application, upload all the documents that are required, and then once they're ready to submit that application, it'll go to the RCO to certify that. And then any user can make the payment. So the RCO, the DRO, the engineer as data entry or submitter, any of those designated users can make the payment for the ATC permit. And then once those steps are completed, then it'll be sent to us for review. I've also included a link that kind of goes into more detail on some of those MyDEQ user roles and responsibilities. So an overview of how everything works now with the MyDEQ portal. Approval to construct, approval of construction, and time extension applications are all submitted on MyDEQ. Exemptions and forlog applications are still submitted through email. So we still have the paper form for those, and those will still be sent to our group email. So the public water system or the developer, if there is a developer, creates a MyDEQ account, and they must be listed as the RCO. So the engineer cannot be the RCO. It's important to note it must be the public water system owner or the developer who is listed as the RCO. And then, as mentioned, they can then add the engineering firm with the role of data entry or submitter. If the applicant has any questions specific to MyDEQ, so if they have non-engineering questions, but questions on the portal, we do have a MyDEQ support team that is able to assist with that. Their email is mydeq.support@azdeq.gov. So they are a great resource with any questions or errors that might be encountered while using the MyDEQ portal. They also have created a user guide that walks you through the approval to construct application process on MyDEQ. So that is another helpful resource if it's your first time submitting an ATC through the portal. So now we have an overview of the admin, submittal, and review process. So before the applications get sent to the engineers for substantive review, our admin completes an administration review. So the admin reviews if all the required documents are submitted in the correct format. They'll check the CIDWIS public water system number. They'll create a Trello card with information, and they also create a hard file that has all of the documents saved for us to access. They'll check that the PE license hasn't expired by looking that up online. They'll check if this permit is associated with a notice of violation or a notice of compliance and make note of that. And if applicable, the applicant will address any deficiencies that the admin has found. And then the admin will then, once those deficiencies, if there are any, are addressed, the admin will assign it to one of the engineers on the team, and then the engineer can proceed with their review. So we've included some of the common deficiencies that can cause andons, though of course this is just a few examples. There are a lot of different possible reasons. Every application is unique, but some of the common ones that we have found for causing these delays is that the developer doesn't upload their water service agreement. Another common deficiency is that the construction plans or as-built don't have that PE stamp. The PE stamp does need to be on every single page, and it must be an engineer in Arizona. Another one is having the wrong RCO listed, or having the NSA not submitted. So the NSA does need to be submitted for wells at the ATC stage. And for AOCs, a common deficiency is that the BACT test is not taken within the past year. It's older than a year, and so it's not valid. And so that'll get sent back so that they can provide a more recent BACT test. So once our admin has finished their review, they'll either approve, deny, or the applicant might withdraw the application, and then it's sent to the engineer. We try to have the engineer who reviewed the ATC review the AOC, though that doesn't always happen depending on workload and availability. And I'll pass it over to Stephanie to talk about the overall process.
Yes, thank you, Nicole. So the overall submittal and review process, we have step 1, the MyDEQ application. Payment is received, and then the RCO certifies and reviews the application, and then the application will be logged. Step 2, Nicole discussed in great detail about the administrative review. So if applicable, applicant will address the deficiencies, and then the admin will assign to an engineer. Step 3 is substantive review. I'm an engineer, and so for the ATC application, I'll review the design report and construction drawings, and I'll refer to our Engineering Bulletin 8 and Engineering Bulletin 10, as well as our Arizona Administrative Code and MAG standards and AWWA standards. MAG stands for Maricopa Association of Government Standards. AWWA stands for American Water Works Association. And then, if applicable, the applicant addresses the deficiencies, and the final decision is an application approval most of the time, but it can be a denial or a withdrawal. Next slide, please. So after the AOC is issued, the review engineer submits a new water system facility form to our data team. This form is only required for new wells, new sources, such as springs, storage tanks, chlorinators, and treatment only. This WSF form is not required for water lines, booster pumps, or pressure tanks. The data team would update the Safe Drinking Water database on this website, and this is a screenshot. You, as an operator, may be asked to help in the ATC AOC process. How? For example, in the AOC stage, you may be asked to take pressure readings, bacteriological tests, or chlorination results. Now, for the ATC stage with the design report, you might have the design engineer or the RCO or the developer asking you questions about the infrastructure of the water system in terms of how it is, the maintenance, as well as probably well pump rates, efficiencies, and equipment that need changing out. Next slide, please. Good thing to do before submitting an application through the MyDEQ portal is requesting a pre-application meeting with the engineers. This is available to all applicants and it's free of charge. And it must be requested through our team email listed here. The purpose here is to help identify any deficiencies and improve project readiness. It includes answering specific questions and checking for common deficiencies. But it excludes review of the documents prior to this meeting. So I think it's very helpful to have this pre-application meeting because, as you could see from the MyDEQ process, you'll have to submit a payment for the application. So it does behoove applicants to request this pre-application meeting to save on time and money. Next slide, please. So thank you for attending our presentation. Do you have any questions?
There is a question in here from Monica. She asks, if we are located in Pima County and have PAG standards, do we have to meet MAG standards?
That's a good question. Sorry, I did not clarify it. We typically look at MAG standards as a standard, but yes, any type of local jurisdiction, you're free to use your jurisdiction's standards.
Excellent. I'll give just one more minute here for more questions to come in. Again, you can contact us via email if you download that agenda handout and do have follow-up questions later. We do have another question here from Gloria. Are all of these steps required for a water district that purchases its water from a municipality?
I think it depends on the municipality. The municipality is a PWS, then the PWS would have to fill out those forms. I hope I understood the question correctly.
Gloria, do feel free to follow up if you have additional questions, either here or via email later. A question from Well, let me follow up. Gloria does have a follow up here with more information. She says, we are a new district and purchase our water from Prescott. I suppose she's wondering if they'll need to go through the ATC AOC steps in MyDEQ.
If the Prescott water system is a PWS, then yes. Nicole, did you have any additional information?
Yeah, the public water system, so it sounds like Prescott in this scenario would be the one that would need to complete the ATC and AOC process.
Excellent. And one more question here from Jeremy. Why are no PE stamps required for federal agencies?
This is a little bit trickier to answer, but it is in our rule that there's such an exception. So we could follow up with him on that particular rule if he could give you his email address. Is that okay?
Yeah, perfect. I should be able to get Jeremy's email here, the one that he signed up for the webinar with, and we can follow up that way. Awesome. That looks like all of the questions for now. Do feel free to keep adding more. But Nicole and Stephanie, thank you very much.
Of course, thank you.
So at this point, we will take a 15-minute break here. We'll be back, looks like 10:20. We will resume. Dane Whitmer from Consort Engineering has a presentation for us on the selection and installation of pipes as we continue looking at water distribution systems. So stretch your legs, get a snack, run to the bathroom, whatever you got to do. We will be back at 10:20 for the next presentation. Hello again, everyone. Welcome back. We'll go ahead and get back into things here with our next presentation. Before we do that, before we hop into Dane's presentation, some quick reminders, and I've said it several times, and I'll keep saying it again. Make sure to download the agenda. The agenda is in the materials section there. You can grab that, upload that for your PDHs if you are an operator. And beyond the agenda, there will be a share file, a document being emailed out to all of you this afternoon that will have presentation slides, and it'll also have a little link to a survey so you can give us some feedback. Let us know how we did, if you would have anything you'd like to see in the future. But with that, Dane, I'll pass screen controls to you and have you take it away.
All right, thank you.
Of course, thank you.
Let's see, we want to share the screen. Can everyone see my screen?
Yeah, so far it is your desktop, and there's your presentation. Looks good.
Perfect. All right. So real quick, a little bit about myself. I'm an engineer with about 15 years in the water industry. I will try not to sound like an engineer during this presentation, and so hopefully you'll get some benefit out of what I say and not just be bored to death. I'm an Arizona native, grew up in eastern Arizona on a family farm, Thatcher Safford, and a couple other quips about me. Graduated from the University of Arizona, and many moons ago, or feels like many moons ago, I'm past chair for Arizona Water's Distribution Committee and current Phoenix chapter president and Arizona region liaison for Engineers Without Borders. So I have my hands in a couple of different pots and pies here, and trying to get myself out a little bit more. I've done this presentation a couple of times, and so I apologize if someone's on here that's seen it before, but I'll try to make it as fresh as I can. So some of the topics that we'll go over today is discussions over the pipe types, and design inspection considerations, and lastly, a couple of maintenance topics that we can go over for valves and pipes. So quick, I typically do this in a group setting, but here's a couple of pictures of things that maybe you've seen, maybe you haven't. And so the question typically is, what's your best guess of what each of those are? But we'll kind of move through that. And on the left-hand side there is actually lead pipe that was used by the Romans about 200 BC. And those lead pipes for Rome, they ranged anywhere from about 1/2 inch to 24 inch. Lead pipe was formed by making uniform sheets and then rolling it to the desired radius and then soldering the seams. The other side there is our wood stave pipes, about used in about 1900 and 1911 is when that picture was taken. So a lot of different materials have been used for pipes over the century, and there's been a lot of activity that's occurred. I've kind of put together this this history of pipelines for your kind of thought here. All the way dating back, some of the earliest known pipe, and things can be older when you get that far back. It's just what they've discovered and survived. Clay pipe's been one of the oldest type of pipes used. There's been brick and mortar that were found in the Persian, Macedonias and Minoans. Lead and wood pipe were regularly seen, just as a mark there. Rome fell in the 600s. I don't know if it was exactly because of lead pipe, but maybe that was things. Water has always been a staple of an organized region or community, right? So one thing that made Rome so prosperous is their water system, the ability to have clean water, and even their ability to remove wastewater out of their city and maintain health. We started to see cast iron pipe back in the 1700s. And with the formation of AWWA in the late 1800s, then it was actually standardized in about the start of 1900. Steel tube manufacturing in 1825 started occurring, but it wasn't even steel pipe wasn't even standardized until 1975. Like I said, a lot of different types of pipes here and there. An interesting point here that I like to pull out is the concept of chlorination, right? So 1908 rolls around and the city of Jersey City, New Jersey was having a cholera outbreak. And the sanitation group that was over there started to tell the water companies, like, hey, you need to start figuring this out and getting it worked. There was an engineer back in the time, George W. Fuller. He was trained over in Germany, came and started and learned about chlorination for water systems over there, and started and introduced the first chlorine system starting about then. We started to also understand the pathways for disinfection and bacteria, and so it started to actually have our standards for coliform counts back in 1914. And really, population started to really take off in about the 1920s, 1930s, and that's when you see actually, because of chlorination occurring, that nearly all waterborne epidemics were eliminated. So again, society doesn't evolve without having these basic needs met. It's one thing about Engineers Without Borders that I emphasize, is that if you're living in a community, a society that has to work from day to day to pay their bills, to survive, and a portion of your time is spent just getting water, or if you, again, because you're an hourly or a daily wage person, if you're getting sick from your water source, then you're going to be losing out on potential income. And so without having these things in place, that we're not going to be able to maintain a society. You're going to be in a state of perpetual poverty, just simply by the water. So I commend those people in our industry that maintain our water systems and keep our society moving forward. You're really an unsung hero from my perspective, and want to always say thanks to that. So a couple things we'll go over today, and what you should probably have in your back pocket when it comes to piping knowledge. Understanding the concepts of pipes, pressure class, the working pressure rating, thickness class. Understand how joints are made for the different types of pipes, where to use them, when to use them, the ideas of restrained versus unrestrained. Got a little typo there, sorry. Coatings, linings, how pipe is protected once it's in the ground from corrosion or other environmental impacts. And then what type of corrosion systems can be used and where to use them, and whether your system, your piping system has a corrosion protection, or what kind of might be necessary. Also wanted to introduce, you should have some working knowledge of where to find standards between American Water Works Association, ASTMs, your state, regional, and locals, which all guide the type of materials that are used, how to install them, how to keep things safe and going forward. So let's hop into some types of pipe that we are commonly found in water distribution systems. So ductile iron, probably the most widely known, widely used material. You have what's called the Ductile Iron Pipe Research Association, or DIPRA, and they kind of hold the standards of the forming and material selections that go into ductile iron. You also have AWWA that's involved in it. So ductile iron pipe ranges 3-inch. That's sort of kind of an uncommon size. The smallest size you'll really see is 4-inch, but goes up to 48 inches. Anything bigger than that really gets heavy. You can select some special sizes, and it comes in lengths of 18 to 20 feet, depending on the size that you get. So again, I mentioned this terminology of pressure class, thickness class. So there's pressure classes, and when you're trying to define how strong of a pipe you need, and pressure class is it's more than just what kind of working pressure or what kind of pressure am I going to see the pipe is going to see. It's also a function of how much load, external load, is going to be on that pipe. And so as engineers, we look at how to measure both the internal pressures and the external pressures to determining what kind of pressure class you have. In 1991, DIPRA changed or added pressure classes to their selection. Before, they were a thickness class, you know, a number that ranged from 50 to 56, which was a wall thickness. And so they added in pressure class 150, 250, 350 to seem like it was more in line with other elements of water systems that were being sold, for example, your fittings or valves that might be part of it. So you'll see those other items. So even though it's a pressure class 150, there's actually a lot more that goes into it. For example, when they're considering the thickness of the pipe for a 150 pipe, they'll add in like a 2-to-1 safety factor, and then they'll also add in another 100 PSI to the surge that's associated with, which surge is a whole nother topic. And funny enough, it's like everything on this, you can spend a whole another hour on just specialized topics on each one of these. So joints, you have flanged, bell, spigot, mechanical, grooved end type joints. Standard coatings that you can see is cement mortar lined. Externally, you'll see butamus coated. You can get paints, which are fusion and bonded epoxy, both internal and external. If it's wastewater, you'd hear something like ceramic epoxies. You can get them glass lined, very expensive, very corrosion resistant, but also very fragile, right? Just like glass. And then you can also have your pipes coated with a zinc-rich primer, which help in the corrosion aspect of the pipe. One notion here off to the side is one of my projects that I was part of. This is a 42-inch pipe out in Amman, Jordan, so out there in the Middle East. And this pipe had a blockage in it. And they were confused at what was going on. And the overall shape of this pipeline was a really big inverted siphon over about 15 miles. And so they were, well, what's going to block a 48-inch pipe in sewer? And turns out that the liner, the cement lining, had failed, and all those chunks had settled and got moved to the bottom of the hydraulic or elevation of the pipeline system. That was probably more of a manufacturer issue than it was actually that would actually really occur, but it can go to show that, you know, cement, ductile iron and wastewater is probably not your first choice, but for wastewater, but it works really well and is a lot of industry standard for water distribution. Corrosion protection, we want to be looking at our coatings. You can have it polyethylene encased to try and separate the soil and the pipe. There's also active and passive systems, so anodes, cathodes, and different things that you can attach to the pipe to do it. That, again, whole nother topic. One thing I do want to point out here is the NSF 61. I'm sure you've heard of it, but if you haven't, NSF 61 is an organization, National Science Foundation, and their standard 61 is what the baseline testing essentially states that what products that come in contact with or potentially in contact with potable water will not further contaminate the drinking water itself. So it's drinking water safe is kind of the takeaway term that you want to think of for NSF 61. So a little bit of pros and cons. ductile iron is considered to last about 100 plus years, but we really didn't start installing ductile iron until about the 1950s. So that 100-year, a lot of these statements you might hear from manufacturers, oh yeah, this pipe is going to last 100 years, this pipe is going to last 50 years. A lot of times it doesn't line up with when pipe was started. So there's always a little bit of caveat of what they're considering, you know, this based off of. So 100 years, because cast iron has been shown to, in the right conditions, will last 100 years. But anybody that's worked on piping distribution systems knows that pipe can fail much sooner, and it's all about what kind of environment the pipe is installed in and what kind of installation procedures, the care of installation has gone into these pipes. It has a benefit over steel in that it is more corrosion resistant. It's more ductile, as it says in the name. It has a higher strength, can handle some more poor handling, has good bury depth, and it allows for some joint deflection in its approach. Some of the cons, it is, because it's metal, there's a weight and handling and shipping costs can be higher, and because of that, you have a higher handling cost. Ferrous corrosion always requires consideration, and if anybody has welded before, you can find that ductile iron or cast iron equally are difficult metals to weld and take specialty to consider. So that's why we don't see welding of this pipe. You have these mechanical joints or push-on type joints or other types of external mechanical restraints to hold the pipe together. Or even the idea of your service taps, right? That they're not a welded a bung or a tap like that you're using a saddle or a threaded tap. Next type of product, the next standard in the industry is PVC pipe. There's a couple of different standards out there and different types of pipe to consider. That you have for most distribution systems, you're going to see C909. A newer kind of version is the C900, and the newer version is C909. You may remember a C905 version of pipe out there. That is still, it got changed in about 2017, 2018. That the 905 designation went away, and it was just all wrapped into C900. So C905 is still the same as C900. The difference back then is the size of pipe range was differentiated between the two standards with AWWA. C909 is a different mix. It's still the same strength. The material is stronger, but that means that they can thin out the wall a little bit more on that pipe. So you actually get a little bit bigger ID on a C909 pipe with that stronger material. Schedule 80, Schedule 40 is more of a plumbing or plant item. Schedule 80 is what we'll use. It's the thicker of the two pipes, and you have CPVC or chlorinated polyvinyl chloride, which is more chemically resistant pipe. And everything, the thing to note here is that everything comes in a different format, right? Some are based off of steel pipe, like Schedule 80, Schedule 40. Some CPVC can be based off of copper pipe in the smaller diameters, but you can get it in the IPS type. And then C900 is going to be based off of the ductile iron dimensions. So you'll be able to use ductile iron fittings on your PVC pipe or transition more easily between ductile iron and PVC. So your joints, it's mainly bell and spigot, so slip-on joints. You have, and to restrain this, you have to have external restraints that go over the bells, some mechanical joint fittings, and then there's also this fusible PVC, so much like HDPE. There's a special mix out there. It used to be proprietary. I don't know if it's opened up or the patents expired on it and other people are doing it, but fusible C900 PVC, if you're looking for a completely closed system, typically used in a jack and bore or slip lining type approach. So here's a picture of one of those external restraining harnesses for the joints. So PVC, there are no coatings unless it's going to be exposed to UV, to the sun. So these pipe have no UV resistance. So kind of the idea, if you're getting PVC pipe installed, C900 pipe, especially here in Arizona, and your contractor is letting it sit out in the sun baking, or there's a delay in the project and that pipe is sitting, it needs to be covered. Otherwise, it will become more brittle and lose its strength. So it is corrosion resistant, being a plastics, but it is susceptible in some cases to chemical attack or degradation over time, losing its strength. They call it impregnating of the plastics. And it's more important to know if you're going through areas with a contaminated soil. In most cases, it's not a concern, but I'm sure over many years that the chlorine concentrations can also wear on it at times. You need to be aware of your gasket materials. SBR is probably more of the standard type of material that will come in these, but when it comes to water systems, I myself will always spec an EPDM type gasket, and that's because EPDM has better resistance to chlorine, as opposed to something like NBR, which has other trade names like nitrile butyl rubber or Buna-N. I use that in our wastewater sides of things because it's more resistant to fats, oil, and greases. So a couple of standards to be aware of. AWWA has their standards, and then much like DIPRA for ductile iron pipe, you have Unibel for C900 and other plastic pipes. Pros and cons, again, that caveat is considered to last 50 to 100 years. But I think if I look back at my, let's just go back up to the time frame here. So PVC pipe was invented in 1935 and it was standardized in 1975. So again, it hasn't been in the ground for 100 years yet. So it has some flexibility to it, especially in the smaller diameters. So that's something to always consider. Just because it's plastic doesn't mean that it can bend. There are limitations to it. It's lighter. That means it has a lower cost for delivery and it does allow for some joint deflection. Here's another picture on the right-hand side of another way that PVC pipe can be restrained using these locking threads or cords that you put through it. And then this is an example of fused PVC up here, or C900. Again, probably using it in some type of micro tunneling or jack and bore, or not jack and bore, but slip lining type no dig approach. So some of the cons here, it is fragile. So it doesn't do well with what I call the Billy Bob construction approach, right? It's not going to handle being dropped. It's going to crack, and so you have to take extra care with it. Unlike ductile iron, if you dropped it off the trailer, the loading trailer, more than likely you're going to be okay, outside of maybe compromising your internal coating. You have to have more considerations to your trench backfill, and then because it's light, if you have a situation where you have a monsoon come in, fills your trench up with water, you're going to float the pipe out of it. HDPE is probably one of my favorite types of pipe just because of a couple of things. One, it is highly customizable, and it is a completely restrained system or a completely sealed system. So no joints that are expected to leak. Just like anything, it's susceptible to the level of quality that goes into the fusion process and joining of the pipe and the construction methods. There's a solid wall C906 pipe versus another type of pipe, which is structural profile wall. Solid wall goes up to typically about 60 inches, 64 inches. And then profile wall will take you up to 12-foot diameters. So really using that in specialty cases for low pressure, gravity, everything has its considerations for installation. It does become a little bit of a hectic run to figure out the pipe thicknesses. So again, using the pressure passes that they do, and then you can have it in iron pipe size versus ductile iron pipe size, but that's how things are controlled on the OD. So even though it says it's 30-inch ductile iron pipe size, because of the strength of HDPE, you have to have a much thicker wall to it. So you'll actually reduce the size of your flow path. So if, for example, if you have an 18-inch ductile iron pipe installed, you will need a 20-inch HDPE pipe to get it. Or if you have a 24-inch, you need a 30-inch HDPE. So a lot of things to be considered. It's black for a specific reason. So unlike C900 pipe, HDPE is UV resistant because it is impregnated in its process with carbon. So that makes the plastic, you can have it exposed, you can have it sit out. It's used extensively in mining to get from point A to point B for carriers. It's very resistant to scouring. One caveat to it is that, and the cons here, is that it is permeable to petroleum and chlorinated solvents at all to low concentrations. So if you are running through an area that has a leaking underground storage tank, or that there's a known chemical contamination, you'll be able to know this right when you're digging up your trench and all of a sudden you smell that gasoline smell, that it will actually seep its way through the wall and has potential to contaminating your potable water supply. So it can be used in water, and it's NSF 61 certified in its own right, but you just have to be aware of those conditions. And when you reach those conditions, you'd have to change to a different material. All right, steel pipe is another pipe that is, again, highly customizable. It ranges in a large diameters. It's been a staple for a lot of years in the industry. It comes in many different types of joints, and you can have it completely restrained, being welded or flanged. You can have it with bell and spigot types. And there's a lot of things that go into specifying how this pipe is used. So in my opinion, this is probably the most customizable, but also requires some of the most engineering effort to get it designed appropriately. It has lots of coatings, mostly the paints where epoxies and polyurethanes are used. And so just a little side note, epoxies are good for inside the walls or inside housed, because when epoxy is exposed to sun, it actually will start to create a chalk or a chalky kind of layer. So if your steel pipe is exposed and you have some kind of architectural consideration, epoxy is not the way to go, because over time it'll fade in color because of that chalk coating that kind of gets built up from the UV degradation. So what you'll use for an external is a polyurethane type coating. For bearing, you can have coal tar wrap on the exterior. It can be cement mortar lined and coated. Again, because it's susceptible to corrosion, you have to take in big considerations of how it's coated, and what kind of, corrosion protection systems are being used. Because of, even though it says that it has, 50 to 75 year lifespan, depending on who you talk to, they do need regular inspections because of its potential for corrosion. So even though everything's coated, there still might be something that gets scraped during installation, what's called a holiday or a pinhole in the coating system, and it all starts from there. So again, here's a list of some of the pros and cons to those types of systems. Because of its customizability, that you can get a lot of different configurations for it, and production of installation. And just, I hope one thing that's coming through on this idea of the different types of pipe is that there's no one silver bullet to use, right? Everything has its own pros and cons. But with that, the great thing is that we can design for any of the inadequacies that these pipes might encounter. So as long as we know about them, then I, as an engineer, should be able to design a pretty resilient system that lasts the expected lifetime. So concrete cylinder pipe. These are AWWC 300 reinforced concrete cylinder pipe. There's also pre-stressed concrete cylinder pipe, and then there's also bar wrapped concrete cylinder pipe. The difference between all these, or the concept to kind of go about them, is that they start with a steel shell, and then there is a reinforcement that goes around them. And whether it uses a cord that is stressed during the installation, or that it's more like a cage for like a column, a loose wrap, the 303 type pipe, then it's all coated in cement. So this is an engineered type pipe that's designed to try and reduce the weight of concrete type pipe and use the strength of reinforcing to increase its strength while reducing the weight. So they come in several different types of joints, and we look at these when we have higher pressure, larger diameter type pipes. You can kind of see the cut sections there of how the pipe is kind of formed. You have your internal lining, the shell, which doesn't add, you don't consider that as the strength. The strength comes from the reinforcement. So the bars, the pre-wrapped. And then how you want to make those joints depends on your conditions of what you're going to do. But they come back and they essentially, if it's a kind of a loose, a standard bell and spigot, they come back, I call it a diaper. They'll put a diaper around the pipe joint and they fill it with grout, and that helps protect a corrosion protection layer against the soil. It's really important that you provide regular maintenance on these pipes. So and that involves inspections, right? So here's an example of an inspection for the bar wrap, and there's multiple breaks in that wrap that occur. And if this isn't a pre-stressed condition for this bar wrap, that's where you're losing the strength of the pipe. And so if this pipe has a high pressure, you may not be able to, it may not be able to withstand that pressure any longer, and that pipe would have to be replaced. So a lot of work goes into understanding these. So it's all about protecting the wrapping, and so making sure that the concrete is not itself. That used to be one of the problems, is that it had a lot of alkaline in the cement mixture, and they were corroding the supporting bar wrap. Again, it's supposed to be considered to last 50 to 100 years. It's a very strong type of pipe, or that can be used in these large diameters and can be fully restrained. Some of the cons to it is that it's heavy, and because of those past failures, that it has a lot of poor track records, but it's still used today. and don't use concrete pipe and wastewater. All right, design considerations. A couple of things that I'm going to fly through a couple of things here as we kind of keep on moving on. With design phase, just understand that you can set up how you want your design to occur, but there's certain elements that we want to include the design and we want to be aware of. So in Arizona, it starts out with the basis of design requirements is outlined in our manual, or let's see, what do we call these? The engineering bulletins number 10. Written in 1979, 1978, I'm waiting for a new edition anytime now. And, but in there, it's dictated one by code that we use this, this engineering bulletin to design this for. Distribution system layout. There's also administrative code laws that we have to follow, and in this case, I'm highlighting the idea that there needs to be physical separation between your sewer lines, and your potable water lines, as well as if there's any sewer systems, or my brain's blanking right now, the leach fields, right, off of your septic systems. So there are these laws, and these have been interpreted by local associations of government. So here's, for example, a couple of details by Pima County, and here's one by Maricopa Association of Governments to depict what that law is stating, how we should separate ours. If you're asking me, I would recommend the following items: that all crossings should provide the maximum level of protection to public health. So we prevent these cross connections in the actual design of it. So what we do that by, whenever possible, I'd never cross a water main below a sanitary sewer. And if that happens, I try to be as very considerate as I can of removing any joints within the area or sealing those joints, and that I make those crossings as perpendicular as I possibly can, or making them 90 degrees to each other. Also, so when we cross pipes, I always like to see 2 foot wherever possible, 2 foot or greater, with a minimum of 1 foot when they are close. But I have extra considerations for that when they're closer that way. So here's a couple of the other plan views for those types of crossings. Again, I prefer wherever I can to be as close to 90 degrees in those type. And that then I also, from outside to outside, I'm keeping a minimum of 10 foot from the next possible joint. That way that there is a leak in these pipes and this is a pressure main, that they're not cross-contaminating each other. When you're considering your distribution system, you should always have your own design requirements and plan review checklist. Make sure that if you want to go above and beyond what is required by law, whether it's the type of materials, the selection of vendors, or what have you, that you are using these for any developers to follow, because I have a lessons learned here later that's a nightmare for developer delivered systems. Construction inspections. So after you've designed it, this is just to say there's different ways to deliver the construction of your design project. And so there can be private and public bids. There's your JOC, and JOCs and bids typically go through the design, bid, build order. It's designed, it's bid for, and then contractors are building it. Other progressive type delivery methods are what's called construction manager at risk here in Arizona, or design build. So in each phase here, whether it's in design or in construction, there needs to be a significant involvement by our operators. Whether it be identifying the needs to make the system as maintainable as possible, as well as work through any kind of MOPOs or shutdowns to allow for the construction work to proceed in a safe manner. As well as having times to look at your contractors and see what they're doing, making sure they're installation, because this is kind of the last step of everything, right? And as well as the system might be designed, you know, so this little clip here that I have inside this little quote, this came back from that a 1911 manual for installing wood stave piping systems. It says, regardless, to confine water under pressure and produce tight work requires experience as well as conscientious care in construction. No matter how well the parts may be designed and how simple a matter of the work of assembling the parts may seem to be. So again, if we have the best material, we have the best designer, if it's not installed per plan, per industry standards, you're going to have failures a lot sooner. And that's what we find in our system. Most often why a system will fail. So you as an inspector or having inspectors, they're really kind of the last line of defense for quality control. And we're not there to facilitate a trade of work. It's not, hey, if you do this here, you can do that there. It is to make sure that the plans are being executed to the requirements and to the standard of care that's necessary. Again, we're here to protect our public water supply and ensure society is moving forward. We don't want to skimp on these items. And this another key point here, it's important to maintain our knowledge, and that is through either our GIS system or libraries. But we don't let, if in construction there's a change in construction, we shifted the pipe over 3 feet, we shift the pipe over 3 inches, that is documented. We don't let a mistake exist for the next 30 years because you say, hey, we need to reline this we need to replace this pipe. And we go in and we look and the pipe's not where the plans say. So we did all this design work, we did all this effort, and everything's boots on the ground, and now we have to stop. So maintain those records, whether it's using a GIS system, a library with the red lines, and make sure that if there is institutional knowledge, that we update any of our standard operating practices and our O&M manuals with that information. It's a living document. Maintain it at every step of the way. So a couple of maintenance items here in this last little bit. So pipes are not just a set it and forget it kind of thing. They are they're a contaminant of concern hoarder, meaning that things can build up in them, and over time, if there's ever a shift in the water quality, the water chemistry, there's potential for leaching of things. So if you recall here, a few years pre-COVID, there was Flint, Michigan, right? Flint, Michigan was the act of changing the water source, and that then in turn had a different water quality and chemistry that ended up leaching all the buildup in the piping system that has occurred over decades of time, which then once it reached to any of those lead line pipes, that it started leaching into the water distribution system and be a major health problem. So we have to look at pipes as a maintenance item, and because of these kind of concepts. So we think of pipe maintenance a lot of times as a flushing practice, but flushing, unidirectional flushing is not the answer to everything, right? Because it will only get hydraulically mobile portions of material, things that can easily be picked up, sediments. So here, this person that I've worked with over at Confluence, here's her example of, here them doing unidirectional flushing. And then here's the difference between before and during, what the water looked like from a foam swabbing process. And then there's this other idea of ice pigging, which is essentially making a slushy of ice and shoving it through the pipe or pumping it through the pipe. And it creates kind of a glacier action to help scour the walls of the pipe. So think about flushing, but also be aware that if there's a change in chemistry, you'll have to look at more than just flushing the system. Maintenance can include leak detection. There's internal ways to check for leak detection. This is an old school and still used method of a listening wand, and checking to see if there's a leak through the meter. There's smart balls might be one, or Piper or I2I type devices. That can help with identifying not only if there's a leak or air pocket, but also some of them help with getting the wall thickness. Valves, here we can do, question is, how do we maintain our valves? We're turning our valves once per year, and we can check that off for fire hydrants if we're getting full shut off. There's typically a whole maintenance program that can go into that. We always want to check our ARVs. The ARVs, as well as pressure regulating devices, are active valves, meaning that they're moving. So some valves will be more active than others, which attributes to the wear on those. So make sure, and ARVs are the least checked items probably in the entire system, because they're either in the roadway, below ground, needing confined space entry. And so, but it still needs to be done. These are wastewater valves, but the same idea. You could be leaking, you have a potential for cross-contamination if your valve's leaking. So make sure that that's in there as well. Again, I talked about the PRVs. Kind of running out of time here, but I'll wrap it up. That's kind of where I had things. If we had more time, we'd go over some lessons learned. But yeah, there's a lot of things that kind of go into it, and what have you there. That we can, if you want to talk more about what we're seeing and how we can avoid these in the future, I'm happy to talk further about that. Feel free to reach out to me with any questions, or email me if you need any further assistance.
Awesome. Thank you so much, Dane. I'll give just a minute here if there's any questions in the chat, if you have anything that you'd like to ask Dane at this point, but if not, contact information on the screen if you do want to follow up later. Perfect. Looks like no questions for now, so we will go ahead and move on. I'm going to pass screen control to you, Stephanie, and we'll get into a presentation on fire flow, on hydrant tests. Let me get you that screen control. This will be our final presentation for the morning. So again, thanks everyone for being here. I hope you've got a lot out of it, and I hope you'll continue to get some more information out of our final presentation here. You can take it away whenever you're ready, guys. Thank you.
Hello. We're going to present about fire flow hydrant test, ATC AOC. My name is Stephanie Huang. I'm an associate engineer with ADEQ. I'm also a grade 1 water distribution, water treatment, and wastewater treatment operator. And my co-presenter is Hafez Ahmed. The agenda today, I'll go over ATC AOC permitting. Is a continuation from our last presentation, as well as fire flow requirements and definitions, hydraulic model versus fire hydrant flow test. What is in a fire flow test? A fire flow test example and a design report example. ATC permitting. Here we're looking at relations to water main lines, water main extensions, and development subdivision type of work. This is a screenshot of our MyDEQ portal for the design flow of the system. The applicant will need to input the average design flow in the peak month, as well as the peak daily demand flow and the required fire flow. So the question that you need to ask, are there fire hydrants in the project? If yes, then you'll put a required fire flow. If no, then you'll click on no fire flow demand. As part of our ATC review, the design report will most likely need a hydraulic model output, such as from EPA-NET or WaterCAD, and a fire flow test report. Fire flow requirements from American Water Works Association M31. It's the rate of water flow at a residual pressure of 20 psi and for a specific duration that is necessary to control a major fire in a particular structure. It is quantity equals rate times duration. Definitions from this AWWA manual: average daily demand, or ADD, the average of the total amount of water used each day during a 1-year period. Maximum daily demand, MDD, the maximum total amount of water used during any 24-hour period. Maximum hourly demand, the maximum amount of water used in any single hour of any day. In AWWA M31, determining design flow, we'll first determine the average daily demand, and from there you can determine the maximum daily demand, maximum hourly demand. And there are different requirements for fire flow if for non-sprinklered properties versus sprinklered properties. AWWA says design flow should be based on the maximum hourly demand or the maximum daily demand plus fire flow requirement, whichever is greater. The distribution system should be designed to maintain a minimum pressure of 20 psi at all points in the system under all conditions of design flow. So this is a theoretical type of model, but sometimes as an operator, you may be asked to calculate these numbers actually from the field, and you'll do that from your monthly meter readings. Hydraulic model versus fire hydrant test. The hydraulic model that's typically in the design report looks like an output table, which models the average, maximum daily demand, and fire flow demands, and is calibrated with the existing data. The fire hydrant test is typically included as an appendix in the design report, and it must be less than a year old, or you need to provide further justification, and it's used to calibrate the hydraulic model. Just as an FYI, if your project has a fire hydrant, then you'll need to put a fire hydrant standard drawing in the construction drawings. So what is in a fire flow test? Here you could see that we have R, which represents a residual hydrant, and F, which represents a flow hydrant. In this review, we're looking at static pressure and residual pressure and flow at 20 psi. There are two different types of fire hydrant tests. Well, actually, there's more than two, but the single hydrant test, which is best to analyze water flow capacity at a hydrant for fire emergency, and a 2-hydrant test, which is best to analyze water flow capacity of a water main and can evaluate pressures and flows on a test hydrant. I did mention there's also multiple hydrant tests, but what we typically see in our ATC review is the 2-hydrant test. So definitions from AWWA M17. Flow hydrant. Hydrant or hydrants at which flow is measured. Pitot pressure. Pressure reading obtained on the Pitot gauge during flow test. Residual hydrant. Hydrant where static and residual pressures are measured. Residual pressure. Pressure that exists in the distribution system measured at the residual hydrant at the time the flow readings are taken at the flow hydrants. Static pressure. Pressure that exists at a given point under normal distribution system flow conditions. This is an excerpt from AWWA M17 of a Pitot tube. This is connected to the nozzle of the fire hydrant. ID means inner diameter. So office planning prior to field of doing a fire hydrant test according to AWWA M17. First, you want to review the distribution system maps, if you have any, and determine which hydrants will be used to measure flow and which will be used to measure static and residual pressures. All hydrants should be at roughly the same elevation. Otherwise, you'll need to do some calculations to approximate that. 2, you should review previous tests to estimate the flow and pressures that can be expected. And 3, select a day for testing when your system consumption will be normal and weather predictions indicate that conditions will be reasonable. The operating division should be notified as to the time and location of the test. So operating division, that's you, right? You're the operator, right? Investigate traffic patterns. I mean, this office planning, you as the operator may be involved with this planning as well. Or you may hire a contract to do this fire hydrant flow test for you. So you may be involved with many of these steps. And you need to make sure the traffic patterns will be good for this fire hydrant flow test. 4, you can use a dynamic hydraulic simulation computer modeling of the supply piping or review previous tests to estimate the flow rate and number of flow hydrants that will be needed to achieve the desired pressure drop. Minimum flow requirements that we usually look at our ATC review. So residential 1 and 2 bedroom family bedrooms, 1,000 gallons per minute for 1 hour at 20 psi. That's the minimum. All other types of buildings, commercial, multifamily, 1,500 gallons per minute for 2 hours at 20 psi. If the fire flow that you get does not meet the minimum or is not proposed, you'll need to get a letter from the local fire authority to submit with your ATC application or the design report in the appendix. So this is more information about fire flow requirements. This is from the Arizona Department of Forestry and Fire Management. And this is the website link to get this information. This is a reiteration of what I just said. They get this information from the Arizona State Fire Code, which is from the International Fire Code 2018 edition. And like I had said, is 1 and 2 family dwellings, 1,000 gallons per minute. And other buildings, 1,500 gallons per minute. Again, with 20 psi. And this is a link to the 2018 International Fire Code. So this is an example of a fire flow test. This is just a hypothetical. We want the time, date, and location of the flow test, The reason is usually typically new construction, the location of both of the hydrants, and there's some information that you put down here. For example, the two different hydrants, the plateau pressure, the fire flow, static and residual pressures, and the total available flow, and your name. So in this case, you could see that the date here is not recent enough. 2020, it will be our deficiency, and we will let the applicant know you need to submit a more recent fire flow test, or like Nicole said in her presentation, will require the fire flow test at the AOC stage. So the references I discussed in my presentation about AWWA M17, which are the installation, field testing, and maintenance of fire hydrants. This is the manual that you could read for more in-depth information, as well as M31 distribution system requirements for fire protection. I did not discuss today about NFPA 291, the recommended practice for water flow testing and marking of hydrants, but that's also a very interesting reference to look at. I've never done a fire flow test before, so that's why I would recommend that you look at these manuals. Also, it's important to look at the videos too. You're a water operator, right? So it's important that you can see on the video how people actually do this type of testing. So I put and shared some links to some interesting videos for you to look at. So now I'll hand it off to my coworker, Hafiz Ahmed. He'll be going over a design report example.
I don't believe we can hear you quite yet, Hafez. Let me see. Yeah, it might be worth leaving and rejoining real quick, and making sure you're selecting the mic that's working there. If you do have any questions for Stephanie in particular while Hafez works out the microphone, feel free to drop those now. It'd be a good time for them.
Hey, can you hear me now?
There you are. Yeah, you sound good.
Sorry.
No worries.
Okay. Thank you, Stephanie, and thank you everyone for joining us today. Now, let us take a look at an example fire flow analysis results and modeling simulation in WaterCAD model. Like Stephanie said, you can use other models, for example, EPA net as well. So this picture is a diagram of the pipe network, where you can see these blue lines and green lines and their dashed lines. These are some of the example proposed and existing water lines in WaterCAD model. Next slide, please. So what do we want to see the fire flow test results? This is a typical example that Stephanie already showed to you a couple of minutes ago, but I would like to emphasize a few important points here. First is the date. Usually fire flow test results needs to be 1 year old but if it exceeds more than 1 year, we typically require to have a new fire test results, which is less than 1 year old, or a support letter from the local fire authority that states that the fire results is good or applicable as of today. And another important point is the residual pressure in the control hydrant, which is when the flow hydrants in active conditions. Here is the residual pressure. An example is 66 psi, which is good because it meets the minimum requirement 20 psi. So we need to see that number at least 20 psi or above. And the third important point is the flow rate, which is the GPM here at 20 psi. So this number needs to meet the calculated demand or at least exceed it. Next slide, please. So what flow scenarios or condition we would like to simulate in model, for example, WaterCAD? So these are the 4 scenarios we typically see in the fire flow test results. First one is average daily demand conditions, then maximum daily demand, peak hourly demand, and finally the maximum daily demand plus fire flow demand. I will show you some of the results in a tabular format for junction and pipe because these are the most commonly looked in component where we would like to see if there are any failed nodes or junctions or pipe. However, you can generate these results for reservoir, fire hydrant, and sometimes for pump as well. Next slide, please. So this table is an example of results that is generated for junctions for the average daily demand conditions. So if you look at the last column, the pressure distribution at different junctions, it tells you that the pressure is approximately 90 psi, which is good because it is meeting the minimum requirement 20 psi. Next slide, please. So this table is for generated the pipe network, different pipe network for the same average daily demand conditions. So in addition to pressure, we'd like to see the velocity distribution at different networks. Industrial practice is not to exceed water velocity 10 feet per second. The reason is if it exceeds 10 feet per second, the system might fail. That's why we recommend to install some of the pressure reducing valve or pressure relieving valve at the section of concern that exceeds the velocity 10 feet per second. Next slide, please. So similar tables for junctions, but at a different flow condition, which is maximum daily demand. So it's again, if you look at the pressure distribution, it's same that approximately 90 psi at different junctions, which is also meeting the minimum requirement 20 psi. But I would like to emphasize one important point here. According to Engineering Bulletin 10, if your pressure that exceeds 100 psi at junctions or pipe network, it typically requires to initial some pressure reducing measurements like valve or pressure relief valve as well. Next slide, please. So similar to the pipe network, we'd like to see the velocity distribution within the range that is below 10 feet per second. So this results is also look good because all the velocity at different pipe sections for the maximum daily demand also below the 10 feet per second. So it is good. Next slide, please. So it looks like similar just for a different scenario like peak hourly distribution. So you'd like to make sure that pressure is within range, like it is above that minimum requirement 20 psi and it doesn't exceed 100 psi. If it exceeds 100 psi, you'd like to identify those junctions and try to install some pressure reducing measurement there. Next slide, please. So it's the similar for the pipe network, just to make sure the velocity doesn't exceed the 10 feet per second, and also we would look at the flow that it is meeting the demand. Next slide, please. And this is the final slide for the condition of maximum daily demand and fire flow demand. So in addition to looking at the velocity that needs to below 10 and look at the pressure distributions, and also I'd like to emphasize that the water demand calculations using the simulations. So in the second column, which is fire flow required, or it's calculated, which is the demand, and the simulation, which is fire flow available. So fire flow available in the fire hydrant, that needs to meet the calculated demand or it should exceed. So in this example, we used 1000 GPM, which is a typical example for residential fire flow demand. So the key point of these results is that you want to identify if there are any failed nodes or pipe networks that meets the minimum pressure requirements and it doesn't exceed that maximum velocity 10 feet per second. If it exceeds, you want to install some pressure reducing measurements, and also you want to make sure the available water demand, it at least meets the calculated demand or exceed it. Okay, next slide, please. So thank you everyone again for listening to us. If you have questions now, you can ask us, or if you have more questions you would like to know more, you can always email us at this address. And you can also visit to our website at azedq.gov/facilities review in our safe drinking water section.
Awesome. Thank you so much, guys. No questions at the moment, but I will let you know if any come in here. Let's see. Here's a question. I don't have any hydrants in my system, but I do have fire standpipes. Do these have to be flow tested?
Stephanie, you want to answer these questions?
Okay, can you get some clarification about the standpipe? Is it just for fire flow, or is it also for consumption? I just want to get some clarification on the use of the word standpipe.
I will let you know if we get a follow-up. Just for fire flow.
So his question is again about testing the standpipe?
Correct. No hydrants in the system, but there are standpipes just for fire flow. He's wondering if they have to be flow tested.
We'll have to get back with
Standpipe
the...
is like a storage tank. They're using a storage tank.
It does sound like the building does have sprinklers as well. If you would like, I can pass this email along to you guys and you can take a closer look into it.
Yes, we need to maybe discuss with our team about this question. Thank you.
Okay.
Thank you.
Sounds good. Well, in that case, I'll go back over here. That is the webinar, and I really do appreciate everyone for attending. Do feel free to follow up with any questions that you have with any of our presenters. Reminding you one last time, if you haven't already and you want to get PDHs for this webinar, you can get those 4 PDHs by downloading the agenda, that materials tab there with the little paper clip and piece of paper. You can download the agenda there, and these presentations will be emailed out to you later this afternoon, and the webinar as a whole has been recorded and will be on the ADEQ YouTube channel at a later date here. We do have a survey up on the screen right now. If you could please take the time to scan that QR code and give us your feedback. The survey asks questions about the format here of the webinar, the presenters, the presentations, so on and so forth. Whether or not you fill out the whole thing to completion or just fill out a couple questions, your feedback is really essential. So we would love to hear from you if you want to take a moment. That survey will also be going out in the email later this afternoon with the presentations. But apart from that, do feel free to reach out to the OpCert program if you have any further questions. And we really do appreciate you all for attending today. You have a good afternoon. I'll leave the webinar open for just a minute here in case any final questions come in, but you are free to go. You've attended, and we thank you for it. And with that, I will close the webinar now. Thanks again, everyone.